Imagine a universe that stretches infinitely, its boundaries dissolving into the unknown, housing secrets that defy human comprehension. This vast cosmos is far more than just an endless backdrop. It is a dynamic, ever-evolving realm, teeming with mysteries waiting to be uncovered. From the grand sweep of swirling galaxies to the tantalizing possibility of extraterrestrial life, every cosmic phenomenon challenges our understanding of reality. As we embark on an exploration of celestial bodies and delve deeper into the wonders of our solar system, we will also peer into the unseen forces that govern the very fabric of existence. What drives this universe, this sprawling expanse of stars and galaxies? The Big Bang Theory, one of the most foundational concepts in cosmology, offers a glimpse into the origins of the universe. It proposes that approximately 13.8 billion years ago, all the matter and energy that make up our cosmos existed in a singularity, an incredibly hot, dense point. This singularity suddenly expanded in an event known as the Big Bang, marking the birth of both space and time. From this explosive event, everything we know today began to unfold. The universe, in all its vastness, began to grow and cool, creating the conditions necessary for the formation of subatomic particles. These particles eventually combined to form atoms, marking the first building blocks of matter. In the minutes following the Big Bang, the universe underwent a brief yet crucial period of nuclear fusion, producing the lightest elements, primarily hydrogen and helium, with traces of lithium. Over the course of millions of years, these atoms gathered under the influence of gravity, eventually coalescing into galaxies, stars, and, in time, planets, our own Earth among them. This process of cosmic evolution continued, shaping the universe as we see it today, and our Milky Way galaxy, along with the Earth, is a testament to this long, gradual journey. The evidence supporting the Big Bang Theory is both abundant and compelling. One of the most crucial pieces of evidence comes from the detection of cosmic microwave background radiation, the faint afterglow of the Big Bang itself. This radiation provides us with a snapshot of the universe when it was just 400,000 years old, offering insights into the conditions that followed its explosive birth. Another piece of evidence comes from the observation of galaxies moving away from us in all directions, a phenomenon known as redshift. This observation strongly suggests that the universe is still expanding, much as it was in the moments after the Big Bang. However, the Big Bang Theory is more than just a model for the universe's beginning. It is a framework for understanding its ongoing development. By studying cosmic phenomena, from the formation of stars to the interactions between galaxies, scientists continue to refine our understanding of how the universe behaves over time. This process of discovery helps us to better appreciate the complexity and vastness of the cosmos in which we reside. One of the greatest challenges in understanding the universe is measuring the immense distances that separate galaxies. Astronomers have developed ingenious methods to gauge these staggering distances. One of the most reliable techniques involves the study of light, specifically a phenomenon known as redshift. As galaxies move away from us, the light they emit shifts toward longer, redder wavelengths. By analyzing this shift, scientists can calculate how fast a galaxy is receding, which in turn provides an estimate of its distance from Earth. In addition to redshift, astronomers use another essential tool, standard candles. These are astronomical objects with a known luminosity, meaning their intrinsic brightness is consistent and predictable. One of the most well-known standard candles is the type Ia supernova, a specific kind of exploding star. Because the brightness of a type Ia supernova is constant, astronomers can determine its distance based on how dim it appears from Earth. These supernovae, visible across vast stretches of space, serve as invaluable markers in the quest to map the universe. To extend these measurements over even greater distances, scientists employ what is known as the cosmic distance ladder, a hierarchical approach that combines different measurement techniques for various ranges. For example, parallax, which involves observing a nearby star from two different points in Earth's orbit, is effective for measuring distances within our immediate cosmic neighborhood. These smaller, more accurate measurements then build the foundation for techniques like redshift and the use of standard candles, allowing astronomers to probe ever further into the vast expanse of space. The distances between galaxies are truly mind-boggling, often spanning millions or even billions of light years. Yet, through the clever application of light physics and meticulous observation, scientists are able to create a detailed map of the cosmos, shedding light on the structure of the universe and our place within it. Each measurement, whether small or grand, helps to build a larger picture of the universe, one that continues to astonish and inspire. Among the most intriguing objects in the universe are black holes, mysterious entities that play a pivotal role in the structure and evolution of the cosmos. At the core of a black hole is a region of space-time where gravity is so intense that not even light can escape its grasp. These powerful forces act as anchors, holding entire galaxies together and shaping their evolution. The influence of black holes extends far beyond the immediate vicinity of their event horizons. They serve as essential components in the delicate balance that sustains the cosmic structures we observe today. The exploration of black holes is just one part of the grand cosmic puzzle. As we continue to peel back the layers of the universe, each discovery deepens our understanding of the forces at play and the interconnected nature of all things. Through the study of distant galaxies, the measurement of cosmic distances, and the investigation of the fundamental forces that shape the universe, we are slowly uncovering the secrets of existence. And in doing so, we are not just learning about the cosmos, we are learning about ourselves and our place within the infinite expanse of space and time. Black holes, in many respects, can be thought of as the osmotic force within galaxies, a central, transformative presence shaping the very fabric of their existence. Supermassive black holes, which are commonly found in the centers of galaxies, are truly astonishing objects, capable of weighing millions or even billions of times more than our own sun. These enormous entities possess such an immense gravitational pull that they not only dominate the stars and gas around them, but also have a profound impact on the star formation, the dynamics of galactic orbits, and the very distribution of dark matter within their realm. As gas and cosmic dust spiral towards a black hole, they form a swirling accretion disk. The intense friction and pressure within this disk cause it to heat up, often reaching temperatures that can emit powerful X-rays, which serve as a beacon, revealing the presence of these otherwise hidden cosmic giants. Black holes, however, are not merely passive entities of destruction. They play an integral role in the evolution and life cycle of galaxies. When they consume matter, the process releases an enormous amount of energy, which ripples through the surrounding space. This energy can regulate the rate of star formation by heating the surrounding gas, or at times driving powerful outflows that sweep away nearby material. Such phenomena are crucial, as they prevent a galaxy from overheating and losing its star-forming potential. In this sense, black holes act as both sculptors and architects of their galaxies, guiding their growth and evolution over billions of years. What's even more fascinating is the dual nature of black holes. While they can destroy, they can also foster new creation. The complex interactions between gravity and the intense energy radiating from black holes give rise to dense regions nearby, areas ripe for new star formation. So, in the grand dance of the cosmos, black holes are not simply the harbingers of cosmic endings. They are pivotal players in the ongoing creation and evolution of stars, planets, and galaxies. In the broader scope of galactic evolution, supernovae stand as another cornerstone event. These awe-inspiring explosions are the dramatic result of massive stars exhausting their nuclear fuel, leading to their catastrophic collapse and violent detonation. When a star explodes in such a manner, it releases a vast amount of energy, hurling enormous quantities of material into space. This ejected material is rich in heavy elements like iron, carbon, and oxygen, elements that are vital for the formation of new stars, planets, and even life itself. Supernovae, in their spectacular grandeur, act as cosmic catalysts, compressing nearby gas and dust clouds, triggering new waves of star formation. The energy released during these explosions revitalizes regions of space that might otherwise remain dormant, creating a cycle of destruction and rebirth. This continuous process of stellar death and renewal is essential for the health of galaxies, preventing them from slowly dying out as their matter becomes locked in dead stars or unformed cold gas clouds. Moreover, the heavy elements forged in the hearts of dying stars during these explosions play a critical role in enriching the chemical composition of the galaxy. Elements such as carbon, oxygen, and nitrogen, essential components for life, are distributed throughout the cosmos, seeding the next generation of stars and planetary systems. Without these supernova-driven processes, we would not have the variety of planets, atmospheres, and environments that are necessary for the emergence of life as we know it. Each supernova, then, is not just an end, but an essential chapter in the ongoing story of cosmic growth, diversity, and complexity. The influence of supernovae extends far beyond the immediate shockwaves they produce. The energy from these stellar explosions can alter the gravitational dynamics of a galaxy, influencing the motion of stars and gas. In some extreme cases, the explosion is so powerful that it can propel material from a galaxy at incredible speeds, contributing to the phenomenon of galactic winds. These winds, which can dramatically affect a galaxy's structure and its star formation rate, play a crucial role in shaping the galaxy's evolution over time. Supernovae, therefore, are not mere flashes of brilliance in the vast timeline of the universe. They are fundamental forces that drive the ongoing transformation of galaxies, shaping their very nature and fate. Dark energy, another mysterious and elusive force, adds yet another layer of complexity to our understanding of the cosmos. This enigmatic substance is thought to account for approximately 70% of the total energy content of the universe. Unlike ordinary matter or dark matter, which interact via gravity and can be detected through light and other forms of radiation, dark energy remains impervious to these conventional methods of observation. It neither emits nor interacts with electromagnetic radiation, making it one of the most elusive components of our universe. Despite its invisibility, dark energy is believed to play a crucial role in the accelerating expansion of the universe, driving galaxies apart at an ever-increasing rate. Its presence challenges the very foundation of our understanding of space, time, and the fundamental forces that govern the cosmos. These cosmic events and entities, from black holes to supernovae and dark energy, are all interconnected, weaving together the grand tapestry of the universe's evolution. Together, they form a dynamic, ever-changing landscape in which creation and destruction are not opposing forces but complementary aspects of the same cosmic process. The nature of the universe is defined not only by its visible components but also by the invisible forces that shape its very structure. One of these forces is dark energy, a mysterious phenomenon that has been inferred primarily from its profound effects on the fabric of space itself. The universe is not only expanding, but this expansion is accelerating at an alarming rate, a discovery that has reshaped our understanding of the cosmos. Imagine the universe as a balloon that is constantly being inflated. As the balloon stretches, the galaxies are carried further apart, moving away from one another. In this analogy, dark energy acts like an unseen force, a repulsive energy that pushes against gravity, causing the expansion of the universe to accelerate. Without dark energy, we would expect the gravitational pull of matter to slow down the expansion over time, bringing the universe to a standstill or even reversing its expansion. Instead, the expansion continues to gain speed. In the late 20th century, astronomers observed distant supernovae and found that they were fainter than expected. This unexpected dimming indicated that these supernovae were much farther away than we had originally thought. If the expansion of the universe were slowing down, these stars would have appeared brighter. This observation led to the groundbreaking realization that some unknown force was driving this accelerated expansion. We now refer to this force as dark energy. Although we still have much to learn about dark energy, its impact is undeniable. It has not only changed our perception of how the universe behaves, but it has also forced us to reconsider the ultimate fate of the cosmos. Researchers are continuously exploring new theories to better understand dark energy, including the possibility that its properties might evolve over time, becoming more or less potent as the universe ages. By answering these questions, we move closer to understanding not just the expansion of the universe, but also the very nature of existence within it. In parallel, one of the most significant pieces of evidence supporting the Big Bang Theory is the cosmic microwave background radiation, CMB. This faint glow permeates the universe and serves as a relic of the universe's hot and dense early stages. Since this radiation has been traveling through space for nearly 14 billion years, it offers a unique window into the past, allowing scientists to glimpse the universe as it was when it first cooled enough for light to escape. Detecting and studying the CMB requires highly specialized equipment designed to capture radiation in the microwave part of the electromagnetic spectrum. Instruments like these are sensitive enough to detect the weak signals emitted by the CMB, providing invaluable data about the early universe's temperature, density, and composition. Perhaps the most famous mission to study the CMB was the Wilkinson Microwave Anisotropy Probe, WMAP, which was launched in 2001. WMAP mapped temperature fluctuations across the entire sky, giving us a snapshot of the universe's earliest moments and helping scientists better understand its rate of expansion. These temperature fluctuations tell us much more than just the state of the universe immediately after the Big Bang. They give us clues about how galaxies, stars, and other large-scale structures in the universe began to form. More recently, the Planck satellite took this research even further, providing even more precise measurements of the CMB. Its findings have provided clearer insights into some of the greatest mysteries of cosmology, such as the existence of dark matter and dark energy. The data gathered from instruments like WMAP and Planck have not only confirmed key aspects of the Big Bang theory, but also raised new questions, pushing scientists to rethink existing models and theories. As technological advancements continue and new observational tools are developed, we can expect further revelations about the origins and evolution of the universe, each new piece of data helping us fit together the grand puzzle of cosmic history. Another fundamental concept in cosmology is the phenomenon of redshift, which provides essential clues about the movement of galaxies across the universe. Redshift occurs when light from a distant object moves away from the observer, causing its wavelength to stretch and shift toward the red end of the spectrum. This stretching of light is similar to the Doppler effect that we hear with sound waves. Just as the pitch of a train's whistle drops as it moves away, the light from galaxies shifts to longer wavelengths as they recede from us. The concept of redshift is not just a fascinating curiosity of physics. It is a critical piece of evidence for the expanding universe. In the early 20th century, American astronomer Edwin Hubble discovered a direct correlation between the redshift of light from distant galaxies and their distance from Earth. The farther a galaxy was, the more its light was redshifted, and the faster it appeared to be moving away from us. This observation formed the basis of Hubble's law, which remains one of the cornerstones of modern cosmology. The importance of redshift goes far beyond just providing a method to measure distances. By analyzing the degree of redshift, astronomers can estimate how long it has taken for light to travel from distant galaxies to Earth. This means that when we look at distant galaxies, we are not just observing them as they are now, but also as they were billions of years ago. This ability to observe galaxies in their past allows us to study the evolution of the universe, shedding light on how galaxies, stars, and other cosmic structures formed over time. Together, redshift and the study of the CMB provide us with powerful tools to peer back in time, revealing the universe's earliest stages and its ongoing evolution. Each observation brings us closer to understanding the cosmic forces that govern the universe and the intricate processes that have shaped everything from the formation of stars to the birth of galaxies. As our understanding of these phenomena deepens, so too does our understanding of our place within this vast, ever-expanding cosmos. Redshift is one of the most powerful tools in modern cosmology, offering profound insights into the forces that shape the universe. It plays an essential role in revealing the elusive influence of dark energy, the mysterious force believed to be driving the accelerated expansion of the cosmos. By examining the redshifts in light from distant objects like supernovae and other celestial phenomena, astronomers can unlock crucial information about the mechanics of the universe. These observations provide valuable clues about the formation and evolution of galaxies, helping scientists trace the complex history of cosmic development. As a dynamic and vital concept, redshift has become instrumental in unraveling the intricate complexities of the universe. It continues to expand our understanding of its vastness, age, and underlying structure. Through redshift measurements, researchers are able to piece together the cosmic puzzle, offering a clearer picture of how the universe evolved from its earliest moments to the present day. Quasars, or quasi-stellar objects, represent some of the brightest and most energetic phenomena in the universe. Discovered in the 1960s, these objects initially appeared to be stars due to their intense light emissions, but they are, in fact, supermassive black holes located at the centers of distant galaxies. These black holes actively consume surrounding material, generating immense gravitational forces that cause matter to heat up to extraordinary temperatures. This intense heat produces radiation so powerful that it can outshine entire galaxies, making quasars visible even from billions of light years away. What makes quasars particularly significant in the field of cosmology is their role as cosmic beacons. Because they are located at vast distances, the light emitted by quasars carries information from the universe's youth, sometimes as little as a few 100 million years after the Big Bang. This makes quasars invaluable for studying the early universe, offering a glimpse into the conditions that existed during its formative years. By analyzing the light from quasars, scientists can learn about the formation and evolution of galaxies, stars, and even the intergalactic medium that fills the vast spaces between galaxies. The study of quasars has also yielded critical information about the expansion of the universe. The redshift of quasar light reveals that the universe is continuously expanding, providing astronomers with a way to estimate the rate at which this expansion is occurring. This information contributes significantly to our understanding of cosmic phenomena such as dark energy, which is thought to be responsible for accelerating the universe's expansion. Quasars act as markers in the grand cosmic landscape, enabling researchers to trace the evolution of the universe over billions of years. Their study is pivotal in unlocking the secrets of the early cosmos, providing crucial data on galaxy formation, the origins of cosmic structures, and the fundamental forces that govern the universe's behavior. In recent decades, a remarkable discovery has reshaped our understanding of the universe's structure: the cosmic web. For a long time, scientists assumed that galaxies were scattered randomly across the vast expanse of space. However, new observations have revealed a far more organized and intricate pattern, where galaxies and clusters form along enormous filaments, resembling a vast web-like structure stretching across the cosmos. This cosmic web is composed of both visible matter, such as galaxies, and invisible matter, including dark matter, creating a complex network of structures that governs the formation of galaxies and other cosmic entities. The cosmic web introduces a layer of order to what was once thought to be a chaotic, random distribution of galaxies. Scientists have identified that the web's filaments are densely populated with galaxies, while the vast empty spaces between them, known as cosmic voids, highlight the contrast between the clustered galaxies and the emptiness that separates them. These voids can span hundreds of millions of light years and emphasize the emptiness in contrast to the dense filaments that dominate the web. This interconnected structure is not merely a passive feature of the universe. It actively influences the movement and behavior of galaxies, playing a central role in their formation and evolution. It also impacts the distribution of dark energy, helping to explain its role in the expansion of the universe. The discovery of the cosmic web has marked a monumental shift in our understanding of the universe's organization, revealing that the universe is far more structured and interconnected than we once imagined. The cosmic web not only offers new insights into the arrangement of galaxies, but also helps explain the larger-scale forces at play in the universe's ongoing evolution. By studying this grand network, scientists are better equipped to understand the nature of dark matter, the distribution of galaxies, and the fundamental processes that continue to shape the cosmos over time. Moreover, the cosmic web fundamentally shifts how we understand the history and structure of the universe. It unveils a reality in which galaxies are not solitary, drifting objects within the vast emptiness of space. Rather, they are intricately woven into a vast and interconnected framework, much like threads in an expansive tapestry. This realization underscores the notion that the universe is not a static or isolated entity. It is an ever-evolving system, one where the movements of individual galaxies ripple across the cosmos, influencing their neighbors in profound ways. The flow of dark matter plays a pivotal role in shaping the gravitational landscape, subtly guiding the formation and movement of galaxies. In this context, the cosmic web is more than just a structure. It is a dynamic force that invites us to reconsider the very fabric of the universe. As we delve deeper into the cosmic web, we are forced to confront fundamental questions about the large-scale structure of the universe. What forces have shaped it? How did galaxies come to occupy the positions they hold today? These questions challenge cosmologists to weave together the threads of gravity, dark energy, and the mysterious dark matter into a cohesive framework that not only explains the location of galaxies, but also unravels the story of their origin within this complex cosmic architecture. As astronomical techniques advance, we stand on the brink of new revelations, each offering us a clearer picture of the invisible structures that bind the universe together and shape the very essence of reality. In our exploration of the ultimate fate of the universe, we encounter a range of theories that propose different futures for everything we know. One of the most widely debated concepts is the Big Freeze. This theory suggests that as the universe continues to expand, it will gradually cool, driven by the mysterious force of dark energy, a substance thought to make up a significant portion of the cosmos. As galaxies drift further apart, stars will burn out and the universe will slip into a deep, cold darkness, a cosmic entropy where nothing new is born and the old gradually fades into nothingness. In contrast to the Big Freeze, there's the theory of the Big Crunch, which offers a more dramatic vision of the universe's end. In this scenario, the expansion of the universe could eventually slow, halt, and reverse. The gravitational pull between galaxies, stars, and other matter could cause everything to collapse into a single, infinitely dense point, creating a singularity. This would mark a climactic conclusion to the universe's story, essentially reversing the Big Bang and bringing all matter and energy back to a state of overwhelming density and heat. The Big Crunch presents a vision of cosmic destruction far more violent than the slow, gradual cooling suggested by the Big Freeze. Another compelling possibility is the Big Rip, which envisions a catastrophic end brought on by the continued acceleration of the universe's expansion. As dark energy's influence grows stronger, the force driving the expansion could eventually reach a tipping point, where galaxies, stars, planets, and even atoms are torn apart. The very fabric of space-time itself could be shredded, leaving behind a void, a desolate and empty space where the universe once thrived. The Big Rip introduces a terrifying scenario, one where the fundamental forces that govern our reality become instruments of cosmic annihilation. In addition to these physical theories, there is the more speculative concept of post-biological existence. As the universe continues to evolve, some theorists propose that advanced civilizations may one day harness cosmic energy on a scale we cannot yet comprehend. These civilizations could transcend their biological forms, perhaps transforming into energy-based life, or exploiting the resources of the cosmos in ways that radically reshape their survival strategies. This speculative notion pushes the boundaries of our imagination, prompting us to think not just about the end of the universe, but also about the transformative potential of intelligent life in the far future. Each of these theories serves as a reminder of the profound mysteries that still elude our understanding. The universe, with its complexities and hidden forces, continues to challenge our perceptions, offering glimpses of its secrets that raise more questions than answers. One of the most elusive and intriguing components of this cosmic puzzle is dark matter, a substance that constitutes approximately 27% of the universe's total mass and energy. Unlike ordinary matter, which makes up stars, planets, and even ourselves, dark matter is invisible to the human eye. It neither emits, absorbs, nor reflects light, making it undetectable by traditional means. Yet, despite its invisibility, dark matter exerts a gravitational influence on the visible matter around it, shaping the structure of galaxies and the universe at large. Regular matter, composed of atoms, is the material reality that we interact with daily. It has mass, occupies space, and allows us to see and touch the objects around us. Dark matter, on the other hand, interacts with other matter solely through gravity. This subtle and mysterious force plays a crucial role in understanding how galaxies form and maintain their structure. Observations of galaxies reveal an astonishing discrepancy. They appear to contain far more mass than can be accounted for by the visible stars, gas, and other matter we can detect. This missing mass is attributed to dark matter, which exerts a gravitational pull that helps prevent galaxies from flying apart. The evidence for dark matter is most apparent in the behavior of galaxies and larger cosmic structures. One of the key observations is the rotation rates of galaxies. At the outer edges of galaxies, stars and gas rotate much faster than would be expected based on the visible mass alone. Without the presence of dark matter, these objects would not have enough gravitational pull to remain intact. They would be flung out into space. This anomaly is just one of many that points to the existence of dark matter, a force that shapes the cosmos in ways we are only beginning to understand. As our understanding of dark matter deepens, it promises to reveal more about the universe's most fundamental structures and forces. Yet, for all our advances, the true nature of dark matter remains one of the greatest unsolved mysteries in astrophysics, a puzzle that continues to captivate scientists and ignite our curiosity about the cosmos. In the vast expanse of the universe, light does not simply travel in a straight line. Instead, it bends around massive objects. This phenomenon, known as gravitational lensing, provides invaluable insights into the unseen mass surrounding galaxy clusters. This mass is typically attributed to dark matter, an elusive substance that scientists are still struggling to fully comprehend. Though various candidates for dark matter have been proposed, including weakly interacting massive particles, WIMPs, and axions, none have been conclusively detected yet. As researchers continue their search, exploring dark matter enriches our understanding of the universe, revealing that the majority of it remains hidden from view, waiting for future discoveries to unlock its mysteries. Gravitational waves, another groundbreaking phenomenon, are ripples in the fabric of space-time caused by some of the most violent and energetic processes in the cosmos. When two massive celestial bodies, such as black holes or neutron stars, collide or spiral toward one another, they create disturbances in space-time that ripple outward, creating waves that stretch and squeeze space itself. The detection of these waves provides scientists with the ability to observe cosmic events that would otherwise be invisible using traditional observational methods, such as optical telescopes. The journey to understanding gravitational waves began in 2015 when the Laser Interferometer Gravitational Wave Observatory, LIGO, made its first groundbreaking observations. LIGO's ultra-sensitive instruments are capable of detecting minute distortions in spacetime caused by passing gravitational waves. This discovery opened a new realm of astronomy, providing insights into events like black hole mergers and the explosive deaths of stars. By analyzing the signals generated by these waves, researchers can gather information about the cosmic events that produced them. For example, the distinctive chirp pattern produced by the merging of black holes reveals crucial details, such as their masses and the distance between them and Earth. This new method of studying the universe complements traditional electromagnetic radiation, such as light, and offers a new dimension to our understanding of the cosmos. Moreover, gravitational wave astronomy has the potential to revolutionize our knowledge of the early universe. These waves carry information from the very moments after the Big Bang, potentially offering clues about the conditions that existed in the universe's infancy. As technology advances and more detectors come online, gravitational wave astronomy promises to unveil secrets about the universe that have long eluded our grasp. Antimatter, another profound concept in the study of the universe, holds the key to understanding some of the most fundamental mysteries of physics. It serves as the counterpart to ordinary matter, with every particle in our universe having a corresponding antiparticle that carries the opposite charge but shares the same mass. When a particle collides with its antiparticle, they annihilate one another, releasing energy in the form of high-energy photons, or gamma rays. This fascinating process not only sheds light on the nature of energy and mass, but it also reveals the delicate balance that sustains our universe. Beyond its theoretical importance, antimatter has practical applications that directly impact contemporary science and technology. In the field of medical imaging, for example, positron emission tomography, P, scans use positrons, a type of antimatter, to detect diseases, including cancer. Additionally, antimatter plays a crucial role in particle physics, allowing scientists to recreate conditions similar to those just after the Big Bang and investigate the very foundations of the universe. One of the most intriguing questions in cosmology revolves around the apparent dominance of matter over antimatter. According to current models, the Big Bang should have produced equal amounts of matter and antimatter, but this symmetry seems to have been broken, leaving an imbalance in favor of matter. Understanding this discrepancy could lead to groundbreaking discoveries about the universe's structure, its eventual fate, and the fundamental forces that govern its interactions. As researchers delve deeper into the nature of antimatter, they may soon uncover more secrets that could change our understanding of the cosmos forever. Meanwhile, astronomers have developed a range of advanced techniques to study exoplanets, distant worlds orbiting stars outside our solar system. One of the most successful methods is the transit method, where scientists observe a star's light. When a planet passes in front of its star, it causes a temporary dip in the star's brightness, which can be detected and used to confirm the planet's existence. This method also allows astronomers to determine the planet's size and its orbital period. Another critical technique is the radial velocity method, which measures the small wobbles in a star's motion caused by the gravitational pull of an orbiting planet. These tiny shifts alter the star's position slightly, affecting its light spectrum. By analyzing these changes, astronomers can determine the planet's mass and its distance from the star. These two techniques, transit and radial velocity, complement each other, painting a more comprehensive picture of the types of environments that exoplanets might inhabit. Once potential exoplanets, particularly those within the habitable zone, the region around a star where conditions might support liquid water, are identified, scientists turn to spectroscopy. This technique involves analyzing the light that passes through an exoplanet's atmosphere during a transit. By studying the spectral fingerprints of various elements and molecules, astronomers can gather crucial information about the planet's atmosphere and its potential to support life. The detection of gases like oxygen, methane, or water vapor raises exciting questions about the possibility of life beyond Earth. As observational technologies improve, with the advent of powerful space telescopes and ground-based observatories, the search for exoplanets continues to yield fascinating discoveries. Each new finding brings us closer to understanding not just the composition of these distant worlds, but also the potential for life elsewhere in the universe. With thousands of exoplanets already confirmed and many more discoveries on the horizon, we are entering an exciting era in the quest to find our cosmic neighbors. Gravity, one of the four fundamental forces of nature, continues to intrigue and puzzle scientists. One of the most perplexing anomalies comes from the study of galaxies. When astronomers observe the rotation curves of these massive systems, they find something unexpected. The outer regions of galaxies spin much faster than would be predicted based on the visible matter alone. This discrepancy suggests the existence of an unseen component, which scientists have named dark matter. As our understanding of these cosmic phenomena deepens, the mysteries of the universe unfold in ever more complex and astonishing ways. Each discovery opens new doors, revealing a universe that is far more intricate and mysterious than we ever imagined. Whether it's the bending of light, the ripples of space-time, the strange properties of antimatter, or the distant worlds of exoplanets, these revelations challenge our perceptions of the cosmos and push the boundaries of what we know. And as science continues to advance, we are on the cusp of uncovering even more profound truths that will reshape our understanding of the universe itself. Gravity, in its most familiar form, is something we experience daily, shaping the way we move, how objects fall, and the structure of the world around us. However, when we look beyond the confines of Earth and examine the grand scale of the cosmos, gravity's behavior begins to appear far more mysterious. This is especially evident when we examine the behavior of massive cosmic structures, such as galaxy clusters. These enormous groupings of galaxies seem to defy the conventional understanding of gravity. The mass required to hold such clusters together cannot be fully explained by the visible matter alone, by leading scientists to propose the existence of a yet-to-be-understood substance, dark matter. In fact, dark matter is believed to make up about 25% of the universe, though its true nature remains one of the greatest enigmas of modern cosmology. This observation suggests that gravity itself, at large scales, might not be as straightforward as we once thought. The universe's expansion also challenges our conventional understanding of gravity. For much of the 20th century, astronomers observed that galaxies were not just moving away from us, but were doing so at an accelerating pace. This phenomenon, which became especially apparent in the late 1990s, was entirely unexpected. It seems that the traditional framework of gravity, as laid out by Isaac Newton and later refined by Albert Einstein, could not fully account for this acceleration. The solution to this puzzle may lie in a mysterious force called dark energy, which is thought to make up nearly 70% of the universe's mass energy content. Dark energy seems to drive the acceleration of the cosmos itself, pushing galaxies apart at an ever-increasing rate. The influence of dark energy suggests that our understanding of gravity is still incomplete, perhaps even outdated. But the strange behavior of gravity doesn't stop at the scale of galaxies. On much smaller, more extreme scales, gravity can also behave in ways that challenge our current theories. In particular, in environments where matter is compressed to extreme densities, such as near black holes and neutron stars, gravity appears to behave differently from the predictions of general relativity. These anomalies suggest that we may need a more comprehensive theory of gravity, one that can also incorporate the strange, counterintuitive principles of quantum mechanics. This quest to reconcile gravity with quantum mechanics is one of the most ambitious goals of modern physics. And while scientists have made incredible progress in understanding the individual forces of nature, the attempt to unify them under a single framework remains elusive. The anomalies in gravitational behavior, from the large-scale structure of the universe to the extreme conditions near black holes, suggest that gravity may be much more complicated than previously imagined. These mysteries continue to push the boundaries of our understanding and challenge scientists to rethink the foundations of physics itself. Turning to the quantum realm, quantum entanglement presents another fascinating avenue of exploration that could reshape not only our understanding of the universe, but also how we interact with it. At the heart of quantum entanglement is a strange and powerful phenomenon. When two or more particles become entangled, their states are linked in such a way that the state of one can instantly affect the state of the other, regardless of the distance between them. This instantaneous connection, which Einstein famously referred to as spooky action at a distance, has profound implications for communication and data transmission across vast distances, such as in space exploration. Imagine spacecraft far from Earth, navigating deep within our galaxy or beyond. Quantum entanglement could allow these spacecraft to send information back to Earth instantaneously, overcoming the immense time delays caused by the vast distances of space. This could revolutionize space missions, enabling real-time communication and data transfer. Such capabilities would drastically enhance the efficiency of interstellar communication, enabling more precise control over missions as they venture deeper into space. But the potential applications of quantum entanglement extend far beyond communication. The field of quantum computing, which harnesses the bizarre properties of quantum mechanics to perform calculations at unprecedented speeds, could see tremendous advancements due to entanglement. With quantum computers, we would be able to process and analyze astronomical data far more quickly, opening new doors for discovering and understanding the universe. Complex cosmic phenomena, which might take traditional computers years to analyze, could be deciphered in a fraction of the time. This could accelerate our understanding of everything from black holes to the formation of galaxies. Entanglement also promises to transform the way we collaborate in scientific research. By connecting researchers around the world through entangled particles, we could create a global network for sharing data and conducting experiments. This interconnectedness could lead to more rapid discoveries and foster a deeper sense of collective purpose in humanity's quest to understand the cosmos. In this way, quantum entanglement could not only revolutionize technology, but also strengthen the collaborative spirit of scientific exploration, forging a shared consciousness in our pursuit of cosmic knowledge. Another intriguing area of research involves neutrinos, nearly massless particles that are produced in vast quantities during nuclear reactions in stars, supernova explosions, and cosmic ray interactions. Despite their abundant presence, neutrinos are extremely difficult to detect due to their weak interaction with matter. This makes them both elusive and valuable, as they can provide insights into processes that are otherwise hidden from view. One of the most exciting applications of neutrinos in astrophysics is their role in studying supernovae. When a massive star collapses in a supernova explosion, it releases an immense burst of energy, and in doing so, it produces a staggering number of neutrinos. In fact, a supernova can emit more neutrinos in just a few seconds than the sun will produce in its entire lifetime. By detecting these neutrinos, scientists can gather critical information about the dynamics of the explosion and the behavior of matter under extreme conditions. This not only improves our understanding of stellar life cycles and death, but also provides a window into the fundamental processes that govern the universe. Moreover, neutrinos may hold the key to some of the universe's deepest mysteries, including the nature of dark matter. While much about dark matter remains unknown, some theoretical models suggest that a specific type of neutrino, known as a sterile neutrino, could account for at least part of the invisible mass that makes up the majority of the universe's mass. This link between neutrinos and dark matter could provide the crucial missing piece in our understanding of the universe, helping to explain the vast quantities of unseen matter that seem to outnumber the visible matter by a wide margin. Thus, neutrinos could hold the key not only to understanding stellar explosions, but also to unraveling the mystery of dark matter itself. Taken together, these advancements, from the deep mysteries surrounding gravity and dark energy to the potential of quantum entanglement and neutrino research, are pushing the limits of what we know about the universe. With each new discovery, we are expanding our understanding of the cosmos, and with it, our place within it. These breakthroughs, though still in their early stages, are shaping the future of space exploration and scientific inquiry, pointing to a future where our grasp of the universe may become deeper, clearer, and more interconnected than ever before. Moreover, scientists are now harnessing the power of neutrinos to probe some of the deepest and most perplexing questions in physics. These elusive particles, once thought to be nearly impossible to detect, are now being studied through cutting-edge experiments that capture neutrinos from both the sun and other distant cosmic sources. These experiments have led to groundbreaking discoveries, most notably the phenomenon of neutrino oscillation. This discovery revealed that neutrinos are not fixed in their type, but instead can change from one flavor to another as they travel through the cosmos. The implications of this finding extend far beyond particle physics, challenging our understanding of the very structure of the universe itself. The idea that these tiny particles, which barely interact with matter, could play such a crucial role in shaping our understanding of reality opens new avenues in both theoretical and experimental physics. Neutron stars, on the other hand, are among the most extraordinary and extreme objects in the universe, born from the remnants of massive stars that have undergone a spectacular supernova explosion. When a star of sufficient mass collapses at the end of its life, the outer layers are blown away, leaving behind a dense, incredibly compact core. This core then succumbs to the immense force of gravity, compressing protons and electrons so tightly that they merge to form neutrons, creating a neutron star. This process results in a cosmic object so dense that just a single cubic centimeter of its material would weigh as much as all of humanity combined. Yet, despite their density, neutron stars hold even more bizarre qualities. Their gravitational and magnetic fields are so intense that they warp space and time around them in ways that challenge the very foundation of modern physics. The gravitational pull near a neutron star is an astonishing 2 billion times stronger than the Earth's, distorting the fabric of space-time itself. This immense force can bend light, creating a phenomenon known as gravitational lensing, where the light from distant stars is bent around the neutron star, offering scientists a unique glimpse into the nature of space. Neutron stars also spin at extraordinary speeds, sometimes rotating hundreds of times per second after a supernova. This rapid rotation, combined with their strong magnetic fields, generates powerful beams of radiation, which sweep across space in a manner reminiscent of a cosmic lighthouse. When these beams align with Earth, we observe pulsars, highly regular pulses of radiation that serve as cosmic clocks, helping scientists decode the mysteries of space, time, and fundamental physics. Inside these stars, the conditions are unlike anything found on Earth. The extreme density and pressure allow scientists to study exotic forms of matter that cannot be replicated in terrestrial laboratories, such as superfluidity and superconductivity. Neutron stars serve as a natural laboratory for exploring the most extreme conditions of matter, gravity, and energy, pushing our understanding of the laws of physics to their breaking points. They offer an unparalleled opportunity to study the universe at its most enigmatic and fundamental level. The life cycle of stars, too, is an awe-inspiring journey that illustrates the ever-changing nature of the cosmos. It all begins in the stellar nurseries of the universe, vast clouds of gas and dust that collapse under their own gravitational pull, forming protostars. As these protostars heat up, they eventually ignite nuclear fusion in their cores, marking the start of the main sequence phase. For most stars, this is the longest and most stable period of their existence. For stars like our Sun, this phase lasts for billions of years, during which hydrogen is steadily converted into helium through nuclear fusion. However, as stars like the Sun exhaust their hydrogen fuel, they undergo a profound transformation. Medium-sized stars enter the red giant phase, a dramatic shift during which the star's core contracts and heats up. This process enables the fusion of heavier elements like helium into even heavier ones, such as carbon and oxygen. As the core grows hotter and more compressed, the outer layers of the star expand significantly, turning the star into a colossal glowing red sphere. These red giants can grow to several times their original size, becoming some of the largest stars in the universe. Eventually, the star runs out of helium and other nuclear fuels, signaling the end of its life. For medium-sized stars, the outer layers become unstable and are expelled into space, creating a stunning nebula. The core that remains behind no longer fuses elements and becomes a white dwarf, a small, dense remnant of the once mighty star. This white dwarf gradually cools over billions of years, fading into obscurity. However, it continues to shine faintly, a ghostly relic of its past. Both red giants and white dwarfs play crucial roles in the cosmic cycle of matter. The material expelled during the red giant phase enriches the interstellar medium, providing the raw materials needed to form new stars and planets. The white dwarf, once it has cooled, contributes its elements back to the cosmos, continuing the process of stellar recycling. This interconnected process of stellar birth, death, and rebirth illustrates the dynamic and cyclical nature of the universe, where stars live, evolve, and ultimately return to the cosmic tapestry. Rogue planets, which drift aimlessly through the vast emptiness of space, add another layer of mystery to our understanding of the cosmos. Unlike most planets which orbit stars, rogue planets wander the galaxy without a fixed home. Their solitary existence raises intriguing questions about their origin and nature. Some astronomers speculate that there are more rogue planets in our galaxy than stars, suggesting that the universe may be full of these enigmatic wanderers. What makes rogue planets so fascinating is the wide variety of their sizes and compositions. Some are rocky, resembling Earth or Mars, while others are gas giants akin to Jupiter or Saturn. Yet, despite these differences, what all rogue planets have in common is the absence of a parent star. Without the warmth and light provided by a star, many rogue planets are incredibly cold, with temperatures low enough to render them inhospitable to life as we know it. However, these isolated worlds can also exhibit surprising features. Some may possess thin atmospheres, composed of gases that might have formed through various chemical processes. Scientists have even proposed that some rogue planets could harbor subsurface oceans, warmed by internal heat generated from radioactive decay or residual heat from their formation. This possibility has opened new avenues for considering where life might exist in the universe, even in the most seemingly inhospitable environments. Rogue planets are often thought to begin their journeys as regular planets within a solar system, only to be ejected into the void after a violent gravitational interaction with another celestial body. These events can send planets spiraling into the cold expanse of space, forever separated from their parent stars. The discovery of rogue planets challenges our understanding of planetary formation and evolution, pushing scientists to rethink the processes that govern the birth, life, and death of planets across the universe. In a similarly fascinating category, brown dwarfs occupy a unique position between planets and stars. These so-called failed stars are celestial bodies that are too small to sustain nuclear fusion in their cores, yet too large to be considered planets. Brown dwarfs fill the gap between planets and stars, acting as cosmic bridges in the galactic hierarchy. They are objects of great interest to astronomers, as studying them provides valuable insights into the conditions that separate stars from planets, helping to further our understanding of stellar and planetary evolution. However, the term brown dwarf only offers a partial glimpse into the fascinating nature of these mysterious objects. While they share the same genesis as stars, forming from the collapse of gas and dust within molecular clouds, brown dwarfs are fundamentally different. Unlike stars, they never accumulate enough mass to ignite the fusion of hydrogen, which is the hallmark of stellar energy production. Typically, brown dwarfs possess masses ranging from about 13 to 70 times that of Jupiter, positioning them in a category all their own, distinct from both stars and gas giant planets. While a star is known for its brilliant shine, driven by the ongoing nuclear fusion of hydrogen, brown dwarfs lack the requisite mass to sustain such fusion for any significant length of time. Instead, they primarily produce energy through the fusion of lighter elements such as deuterium and lithium, elements that have much lower atomic weights than hydrogen. This fusion process is fleeting, and as a result, brown dwarfs gradually cool and fade over time. The low temperatures and luminosities of brown dwarfs make them far more elusive than their stellar counterparts. They often go unnoticed in the vast expanse of the night sky, especially when compared to the bright, burning stars that populate the heavens. Even with powerful telescopes, detecting brown dwarfs can be a challenge. Their faintness has led scientists to liken them to giant planets, particularly since some brown dwarfs share a composition similar to that of gas giants, mainly composed of hydrogen and helium. This comparison deepens our understanding of planetary formation, suggesting that brown dwarfs may share key characteristics with the planets that orbit their parent stars. In addition to enhancing our knowledge of planetary systems, brown dwarfs also provide a unique window into the early history of the cosmos. Observations of these enigmatic bodies offer critical insights into the processes that govern star and planetary system formation. They help us better understand the conditions that led to the creation of our own solar system. In this sense, brown dwarfs are not just fascinating objects in the night sky. They are crucial players in the larger narrative of the universe, linking the worlds of planets and stars in an intricate and ever-evolving cosmic tapestry. Meanwhile, pulsars, those remarkable rapidly rotating neutron stars, hold even more profound secrets. These celestial objects emit beams of electromagnetic radiation that serve as invaluable tools for probing the distant reaches of the cosmos. By studying the light emitted by pulsars, scientists can glean critical information about the conditions that existed in the universe shortly after the Big Bang. Pulsars are born from the remnants of massive stars that have exploded in supernovae, and as such, their existence is intricately tied to the life cycles of these stellar giants. One of the most fascinating aspects of pulsars is their incredible precision. Some pulsars spin hundreds of times per second, emitting regular pulses of radiation with such consistency that they can be predicted with astonishing accuracy. This regularity makes them invaluable as cosmic clocks, allowing astronomers to track the passage of time with remarkable precision. By observing the ticking of these cosmic timepieces, scientists can detect the tiniest variations in a pulsar's rotation rate. These fluctuations may be caused by gravitational waves or distortions in space-time, phenomena that can offer crucial clues about the density and distribution of matter in the early universe. Pulsars can also provide insights into the early universe's conditions through their interactions with cosmic background radiation. As they emit their radiation beams, pulsars can reveal the effects of dark matter and dark energy, mysterious substances that make up the vast majority of the universe's mass and energy, but remain largely enigmatic. The study of pulsars is vital in understanding how these dark forces shape the universe's evolution, from the rapid inflationary period shortly after the Big Bang to the formation of the first stars and galaxies. Pulsars serve as both timekeepers and messengers, offering crucial information about the fundamental structure of the universe and the forces that have molded it. As our understanding of these extraordinary objects deepens, so too does our grasp of the universe's origins, expanding the boundaries of human knowledge further into the distant cosmic past. Similarly, comets are often referred to as the ancient relics of our solar system, holding vital clues to its early history. These icy bodies, formed in the cold, remote regions of space, are believed to contain primordial material that dates back to the birth of the solar system around 4.6 billion years ago. As they travel through the cosmos, comets carry with them this ancient matter, offering scientists a unique opportunity to uncover the conditions that existed during the formative years of the solar system. When a comet approaches the sun, it begins to display its magnificent spectacle. Ice within the comet vaporizes, releasing gas and dust that form a glowing halo, or coma, often accompanied by a spectacular tail. This dramatic display is more than just a cosmic light show. It provides scientists with a rare opportunity to study the composition of these ancient materials. By analyzing the gases and dust released by a comet, researchers can gain valuable insights into the building blocks of the solar system, including organic molecules and other compounds that could hold the key to understanding the origins of life. Comets, in their icy, enigmatic nature, offer a glimpse into the early solar system's chemical makeup, providing scientists with clues that may help unravel the mysteries of how life on Earth began. As we continue to study these frozen travelers from the outer reaches of space, we may yet uncover more secrets about the conditions that allowed our solar system to take shape and ultimately support the emergence of life. The orbits of comets offer an extraordinary glimpse into the gravitational forces at play within our solar system, revealing much about the influence of distant, massive bodies. Some comets, known as long-period comets, originate from the Oort cloud, a far-reaching spherical shell that envelops the solar system. These icy travelers often have orbits that stretch far beyond the planets, and their trajectories can reveal subtle yet crucial gravitational nudges exerted by distant stars. Such influences can alter the path of these comets, providing scientists with vital clues about the deeper, often invisible dynamics of our cosmic neighborhood. Through the study of these enigmatic objects, astronomers are able to piece together a narrative written in the stars, a story that dates back to the early days of the solar system. Comets, made of ice and dust, preserve ancient materials from the birth of our planetary system, and by studying them, we gain direct access to the solar system's infancy. These visitors from the distant reaches of space do not merely shed light on the past, they also enhance our understanding of the processes that shaped our own planet, enriching our grasp of the broader cosmic history that eventually led to the emergence of life on Earth. In a similar vein, the study of extreme exoplanets, planets located outside our solar system, offers valuable insights into the diverse processes of planetary formation and evolution. Some of these exoplanets exist in incredibly hostile environments or possess unusual characteristics that challenge the traditional models of planetary formation. Take, for example, the discovery of hot Jupiters, gas giants found orbiting perilously close to their parent stars. These planets, which defy conventional expectations by being so near to their stars, hint at the significant role planetary migration plays in shaping solar systems. Hot Jupiters form in the cooler, more distant regions of their systems, but due to complex gravitational interactions, they are later pulled in toward their stars. This phenomenon, known as planetary migration, helps astronomers understand the intricate dynamics governing the architecture of planetary systems. As scientists delve deeper into the study of extreme exoplanets, they begin to uncover a variety of fascinating planetary conditions. Planets with molten surfaces, like lava worlds, offer a window into environments that emerge from the intense heat of a star's proximity. Such extreme conditions reveal how the composition and structure of a planet are shaped by both its formation environment and the energy it receives from its parent star. These findings, in turn, force scientists to reconsider their assumptions about how planetary systems form and evolve. In addition to physical attributes, the chemical makeup of extreme exoplanets offers more clues. The presence of particular compounds in their atmospheres, such as water vapor, carbon monoxide, and even metals like titanium, provides valuable insights into the material building blocks available in distant solar systems. Each discovery serves as a natural laboratory, helping astronomers refine their models of planetary formation. Through the study of these distant worlds, researchers gain a better understanding of the myriad possible outcomes that can arise during the process of planet formation, offering a clearer view of the complexity and variety found in planetary systems beyond our own. The study of exoplanetary atmospheres, especially those of distant worlds outside our solar system, is a cutting-edge field that combines advanced technology with innovative scientific techniques. One of the most powerful tools astronomers use is spectroscopy, a method that analyzes the light passing through or reflecting off a planet's atmosphere. When a planet transits its host star, meaning it passes directly in front of the star from our point of view, some of the star's light filters through the planet's atmosphere before reaching Earth. This interaction creates a unique spectral signature, or fingerprint, because different elements and molecules absorb specific wavelengths of light. By studying these signatures, scientists can determine the atmospheric composition of these distant planets, revealing not only the types of gases present, but also important details about their temperature, pressure, and potentially even seasonal changes. For instance, the detection of gases like oxygen, methane, or carbon dioxide could indicate the presence of chemical processes that might be linked to biological activity. These gases, which are often associated with life on Earth, raise intriguing questions about the potential for life elsewhere in the universe. To refine their observations, astronomers rely on powerful telescopes both on Earth and in space. Instruments like the Hubble Space Telescope and the upcoming James Webb Space Telescope are designed to provide the high-resolution data needed to study distant exoplanets in unprecedented detail. New techniques are also being developed to reduce the interference caused by starlight, allowing for clearer observations of these planets. As technology improves, so too will our ability to study the atmospheres of exoplanets, bringing us closer to answering one of humanity's most profound questions. Are we alone in the universe? Super-Earths, a class of exoplanets that are larger than Earth but smaller than gas giants like Neptune, have captured the imagination of scientists and the public alike. Typically, these planets range in size from 1 to 10 times the mass of Earth, and they possess intriguing characteristics that make them ripe for study. One of the most exciting aspects of super-Earths is their potential to support conditions that might be conducive to life. These planets come in various compositions. Some may have rocky surfaces similar to our own planet, while others may be enveloped by thick atmospheres rich in hydrogen or helium. This diversity has led to important questions about their formation and evolution, offering a glimpse into the wide variety of planetary systems in the galaxy. What makes super-Earths particularly fascinating is their potential to exist within a star's habitable zone, the region where temperatures are just right for liquid water to exist on a planet's surface. As water is a critical component for life as we know it, the possibility that super-Earths could harbor liquid water is a tantalizing prospect in the search for extraterrestrial life. The discovery of these planets, especially by missions such as the Kepler Space Telescope, has reignited interest in the possibility of finding planets with climates and conditions similar to Earth. With each new discovery, astronomers and astrobiologists are gaining a better understanding of how life might arise elsewhere in the universe. Finally, binary star systems, where two stars orbit a common center of mass, present a unique challenge to our understanding of celestial mechanics. In these systems, the gravitational interactions between the two stars can create highly complex orbital patterns that differ significantly from those seen in single-star systems. Depending on the sizes and masses of the stars involved, the system's dynamics can vary greatly. Some binary systems feature stars of roughly equal size and mass, while others have a massive star paired with a much smaller companion. These interactions can lead to fascinating phenomena like mass transfer, where one star pulls material from its companion. This process can alter the star's evolutionary paths and lead to dramatic transformations, such as novas or even supernovae. The study of these gravitational interactions is not only vital for understanding the life cycles of stars, but also provides critical insights into the ultimate fates of these stars, which may end as neutron stars or black holes. Each binary star system offers a unique natural laboratory for exploring the complexities of stellar evolution, adding another layer of depth to our understanding of the cosmos. Moreover, binary star systems provide astronomers with an invaluable tool to accurately measure the masses of stars, something that remains difficult to achieve with solitary stars. By closely monitoring the orbital movements of these paired stars, scientists can apply Kepler's laws of planetary motion to calculate their masses. This process offers a level of precision that reveals the underlying forces at play in these celestial bodies. Understanding the mass of a star is of paramount importance. It directly influences the interpretation of its life cycle and the fundamental physics that govern its birth, evolution, and eventual demise. It enables us to test and refine theories of stellar evolution in ways that isolated stars simply cannot, providing a clearer picture of the stellar life cycle. Furthermore, the study of binary systems extends beyond the stars themselves, enhancing our broader understanding of the universe's structure and history. The mutual gravitational influence between the two stars creates a unique cosmic laboratory where scientists can explore the mysteries of dark matter, the dynamics of galaxies, and even the expansion of the universe. Binary star systems serve as both complex puzzles and revealing windows into the intricate workings of celestial mechanics, constantly reshaping our understanding of the cosmos. Mars, too, has long captured the fascination of scientists and space enthusiasts alike. Its mysteries continue to ignite curiosity, inspiring researchers across the globe. Perhaps the most captivating enigma lies in the question of water, past and possibly present on Mars's surface. Rovers and orbiters have provided evidence that liquid water once carved through the planet's valleys, and that water is now locked away in the polar ice caps, with the possibility of it lurking beneath the surface. The tantalizing question remains, could microbial life have once thrived in those ancient rivers? And if so, might any traces of life still persist in the planet's depths, hidden from view for billions of years? Another significant mystery surrounding Mars is its atmosphere and climate history. Once believed to have been a warm and hospitable environment, Mars today is a cold, dry desert with a thin atmosphere composed primarily of carbon dioxide. Scientists are working diligently to understand the processes that led to the loss of the thick atmosphere that might have once supported liquid water on the surface. Understanding this transition could unlock critical clues, not just about Mars, but about the broader history of our solar system and the potential for climate evolution on Earth itself. The planet's geology is equally enigmatic. Gigantic volcanoes, like Olympus Mons, and enormous canyon systems, such as Valles Marineris, raise profound questions about Mars's geological history. What forces led to the formation of such massive features, and why does Mars exhibit such stark contrasts to Earth? By studying Martian geology, scientists aim to uncover the planet's volcanic activity and tectonic processes, potentially revealing broader insights into planetary formation and evolution across the solar system. Looking ahead, the possibility of human exploration of Mars challenges both our technological limits and our imagination. Questions abound about how we could sustain human life on the Martian surface, what technologies would be needed, and how we could overcome the planet's hostile environment. Most intriguing of all, however, is whether we will be the first living organisms to set foot on Mars. As future missions and even the idea of colonization take shape, each new discovery adds to the intrigue, making Mars a focal point for hope, challenge, and curiosity for generations to come. Turning our gaze further into the outer reaches of the solar system, Neptune and Uranus, often referred to as ice giants, stand apart from the other planets. Unlike the gas giants, Jupiter and Saturn, which are composed mostly of hydrogen and helium, these two planets have a significantly higher proportion of volatiles. These substances include water, ammonia, and methane, giving them their icy interiors and unique atmospheric characteristics. One of the most striking differences between the ice giants and the gas giants is found in their atmospheres. While Jupiter is known for its vibrant, swirling clouds of red, yellow, and white, Neptune and Uranus exhibit a more subdued palette of blues and greens. This distinctive coloration is a result of methane gas in their atmospheres, which absorbs red light and reflects blue wavelengths back into space, giving the planets their characteristic hues. Neptune, in particular, is known for its dynamic atmosphere, with some of the most intense winds recorded in the solar system. Uranus, by contrast, has a relatively calm atmosphere shrouded in a haze of clouds. Another fascinating feature of these planets is their unusual axial tilt. Uranus is particularly remarkable in this regard, as it rotates on its side with an axial tilt of approximately 98 degrees. This extreme tilt causes Uranus to experience some of the most dramatic seasonal changes in the solar system. The planet's peculiar orientation has sparked ongoing research into its formation, with scientists eager to understand how such a unique characteristic came to be. In contrast, Neptune's axial tilt is more conventional, yet the planet still experiences a complex and ever-changing climate, with storms and shifts that continue to puzzle researchers. Both Neptune and Uranus hold key insights into the processes that shape planetary atmospheres, the dynamics of ice giant formation, and the broader history of our solar system's evolution. Studying these two distant planets helps broaden our understanding of the diverse worlds that exist within our cosmic neighborhood, offering valuable lessons about planetary science and the forces that govern the formation of celestial bodies in the outer reaches of space. Beneath the thick, swirling atmospheres of Neptune and Uranus lies a starkly different internal structure compared to the familiar terrestrial planets such as Earth and Mars. These two ice giants, shrouded by their dense gaseous layers, are thought to harbor a mantle made up of volatile substances, including water, ammonia, and methane. This icy outer shell, surrounding a solid, rocky core, categorizes them as ice giants, setting them apart from the gas giants like Jupiter and Saturn. Their composition reveals a deeper, more mysterious aspect of planetary formation, broadening our understanding of the varied types of planets that exist in our solar system. The uniqueness of Neptune and Uranus not only challenges our concept of what planets can be, but also highlights the vast, uncharted territories still awaiting discovery in the expanse of the cosmos. These planets offer a glimpse into the complexities that define the outer reaches of our solar system. Meanwhile, Jupiter, the gas giant at the heart of our solar system, is home to one of the most iconic natural phenomena, the Great Red Spot. This massive storm, larger than the Earth itself, has been raging for at least 300 years, and its continuous existence is a testament to the dynamic and ever-changing atmosphere of the gas giant. Spanning approximately 1.5 times the diameter of Earth, the Great Red Spot's striking red hue has long fascinated scientists who believe it is the result of complex chemical reactions occurring in Jupiter's upper atmosphere. These reactions involve substances like phosphine and ammonium hydrosulfide, which contribute to its reddish tint. Unlike storms on Earth, which have relatively short lifespans, the Great Red Spot persists due to Jupiter's unique atmospheric conditions. The planet's massive size, its composition primarily of hydrogen and helium, and its rapid rotation all play a role in sustaining the storm, preventing it from dissipating. The lack of land masses and the strong winds of Jupiter ensure that the storm remains a stable, enduring feature of the planet's atmosphere. However, the Great Red Spot is not completely static. In recent decades, observations suggest that it has been gradually shrinking, raising questions about its future. This shrinkage is part of the broader atmospheric dynamics at play on Jupiter, where powerful jet streams and fluctuating thermal conditions continually reshape the weather patterns. The changes in the storm's size and intensity offer scientists a unique opportunity to study the fundamental processes that drive atmospheric behavior. not just on Jupiter, but across other gas giants and even on Earth. Understanding the mechanics of the Great Red Spot could provide critical insights into planetary weather systems, improving our comprehension of atmospheric dynamics on a cosmic scale. As such, the Great Red Spot serves as an invaluable natural laboratory demonstrating the intricate and powerful forces at work within planetary atmospheres. Saturn, with its mesmerizing rings, presents another remarkable feature in our solar system. The rings, made up of a mixture of tiny ice grains and larger chunks of rock, are not only a beautiful sight, but also a treasure trove of scientific insights. The structure and composition of these rings suggest that they may be the remnants of moons torn apart by Saturn's immense gravitational pull, or perhaps debris that never coalesced into a full-fledged moon. These rings offer a unique opportunity for scientists to study processes that resemble the chaotic conditions of the early solar system, when small particles collided and merged, eventually forming larger planetary bodies. By examining the interactions of these ice and rock particles, whether they collide, shatter, or merge, scientists can gain a deeper understanding of the processes that might have been involved in the formation of planets. Furthermore, the gravitational pull of Saturn's many moons plays a significant role in shaping the structure of the rings. The moons carve out gaps within the rings and create waves, illustrating how celestial bodies can influence their surrounding environments. This ongoing interaction between moons and ring particles provides a window into the dynamic and ever-evolving nature of Saturn's ring system, offering clues about the planetary evolution that shaped the solar system over billions of years. The composition of the particles within the rings also offers critical clues about the material environment during the solar system's formation. The prevalence of water ice in the rings suggests that the particles originated in colder regions, while the presence of other elements reveals a diverse and varied environment. This information helps scientists piece together how planets like Saturn could have developed their unique characteristics, providing a clearer picture of how our solar system came into being. Lastly, recent discoveries concerning Venus have reignited interest in the planet, particularly regarding its climate and the broader implications for studying climate change. Venus, often referred to as Earth's twin due to its similar size and composition, harbors a thick atmosphere dominated by carbon dioxide. This heavy atmosphere has led to an extreme greenhouse effect, causing surface temperatures to soar to levels hotter than those found on Mercury, the closest planet to the Sun. The study of Venus, particularly its inhospitable surface conditions and its atmosphere, provides a crucial point of comparison for understanding the impact of greenhouse gases on planetary climates. In many ways, Venus serves as a cautionary tale, offering valuable insights into the potential future of Earth if current environmental trends continue unchecked. Understanding the climatic history of Venus not only deepens our knowledge of the planet itself, but also informs the global conversation about the health and sustainability of our own planet. Each of these planets, Neptune, Uranus, Jupiter, Saturn, and Venus, offers a distinct perspective on the variety and complexity of planetary systems within our solar system. Their unique features, from icy mantles to persistent storms and magnificent rings, remind us of the many mysteries that remain hidden, waiting to be explored. As we continue to probe deeper into the cosmos, each discovery brings us closer to understanding the broader processes that govern the formation and evolution of planets, stars, and solar systems. However, the recent detection of phosphine gas in the atmosphere of Venus has sparked intense curiosity among scientists. Phosphine is a compound typically linked to biological processes here on Earth, where it is produced by anaerobic microbes. The very presence of this gas on Venus, a planet long considered inhospitable to life, raises important questions about its origin. While the exact source of phosphine remains a topic of ongoing debate, its discovery on Venus has ignited new conversations about the potential for life beyond Earth and the unknown chemical processes that might be occurring in its dense, acidic clouds. This finding opens up a wealth of intriguing possibilities for understanding Venus's atmospheric dynamics and climate. As scientists continue to explore these new data, they begin to reconsider what we know about atmospheric chemistry, especially in extreme environments like Venus's. Such discoveries could prove vital in refining our models of planetary climate systems, not just for Earth, but potentially for exoplanets in distant star systems that may harbor similar atmospheres. In a broader context, these insights are shifting our understanding of how different elements and compounds behave under the immense pressure and heat of a planet like Venus. The cloud layers of Venus themselves hold further secrets that continue to capture the attention of planetary scientists. These clouds, largely composed of sulfuric acid droplets, have long been studied for their unique chemical properties. But recent observations suggest that they could be home to chemical processes that were previously unknown, processes that could shed light on the broader workings of planetary atmospheres. If further research supports this, Venus may offer scientists a rare opportunity to understand the mechanics of weather systems and chemical interactions in conditions far more extreme than those found on Earth. As scientists delve deeper into the study of Venus's atmosphere, the implications extend far beyond our own planet. The atmospheric chemistry of Venus could provide important clues about how to study the atmospheres of exoplanets, many of which orbit stars far older than our Sun. Understanding the climatic processes on Venus could help refine the tools we use to identify planets that might be capable of supporting life. These discoveries, in turn, might one day offer us a glimpse into the possibilities for life beyond Earth. In addition to its atmospheric mysteries, Venus's geological features are offering scientists another avenue for exploration. With its vast plateaus and the potential for volcanic activity, Venus presents a fascinating comparison to Earth's geological history. By studying these features, scientists hope to gain insights into the ways different planetary environments respond to similar forces, including volcanic eruptions and tectonic shifts. Such comparisons can offer important lessons in understanding Earth's own evolving climate and how planetary bodies interact with the forces of nature over geological timescales. As our knowledge of Venus grows, particularly through upcoming missions scheduled for the coming years, we are on the cusp of groundbreaking discoveries. Each new revelation about Venus draws startling parallels to the climate challenges we face on Earth, underscoring the importance of planetary stewardship and deepening our awareness of how our own climate might evolve. In many ways, Venus serves as both a mirror and a laboratory, allowing us to explore the extremes of planetary environments and offering invaluable lessons in our quest to safeguard the future of life on Earth. Beyond Venus, the asteroid belt, situated between Mars and Jupiter, offers yet another fascinating aspect of our solar system's history. The belt is composed of rocky bodies that never coalesced into a full-fledged planet, and these remnants provide an intriguing window into the early solar system. The asteroids themselves are essentially leftover materials from the solar system's formation, dating back over 4.5 billion years. By studying these rocky bodies, scientists can glean important insights into the conditions that prevailed during the birth of our solar system, helping to refine our understanding of planetary formation. The asteroid belt contains a diverse range of materials, from rock to metal, and some of these objects may even harbor traces of organic compounds or water ice. These compounds could represent the building blocks of life, thus offering clues to the chemical precursors that may have been present during the early stages of Earth's development. Asteroids thus act as time capsules, preserving features that have been lost on Earth and other planets due to their geological activity. One of the key advantages of studying asteroids is that, due to their smaller size, they experience far less geological activity than larger celestial bodies. As a result, asteroids retain a record of impacts that date back billions of years. By examining these impact craters and the composition of asteroids, planetary scientists can reconstruct the early environment of the solar system and gain insight into how these objects interacted with the planets around them. Missions like NASA's Dawn, which studied the dwarf planet Ceres and the asteroid Vesta, have provided invaluable data about the asteroid belt. These missions have not only helped fill gaps in our understanding of how planets and smaller celestial bodies form, but have also given scientists a clearer picture of the materials that were present during the solar system's infancy. Far from being just a scattered field of rocks, the asteroid belt is a treasure trove of information that deepens our understanding of the cosmic history that eventually led to the formation of Earth and the conditions necessary for life. Among the many fascinating bodies in our solar system, the moons of Jupiter and Saturn, specifically Europa and Enceladus, have become central to the search for extraterrestrial life. These moons have garnered significant attention due to compelling evidence suggesting that beneath their icy surfaces, they may harbor oceans of liquid water, an essential ingredient for life as we know it. Europa, one of Jupiter's largest moons, is particularly intriguing. Its surface is covered with a thick layer of ice, beneath which lies a vast ocean. The moon has a thin atmosphere composed of oxygen, and there is evidence to suggest that this ocean may come into contact with Europa's rocky mantle. Such an interaction could create a chemical environment similar to that found in Earth's deep-sea hydrothermal vents, where life thrives despite the absence of sunlight. The presence of water, combined with potential energy sources like those found in these deep-sea ecosystems, raises the possibility that microbial life could exist in Europa's depths. Enceladus, Saturn's moon, presents a different yet equally fascinating case. Known for its geysers, which spew plumes of water vapor and organic molecules into space, Enceladus is another prime candidate for the search for extraterrestrial life. These plumes suggest the existence of ongoing hydrothermal activity on the ocean floor, providing the necessary conditions for life. The combination of liquid water, heat, and organic compounds makes Enceladus an environment where life could potentially thrive. Studying these moons of Jupiter and Saturn does more than simply enhance our understanding of where life might exist beyond Earth. It challenges the very definition of habitability. As scientists explore the extremes of our solar system, they are reshaping our understanding of biology, life, and the potential for organisms to survive in environments vastly different from those on Earth. Upcoming missions to Europa and Enceladus will bring us closer to answering one of humanity's most profound questions: are we alone in the universe? In a completely different realm, solar eclipses provide rare and valuable opportunities to expand our knowledge of both the sun and the moon. During a total solar eclipse, the moon completely obscures the sun, casting a shadow across the Earth. This phenomenon allows scientists to observe the sun's corona, its outermost atmosphere, which is normally hidden from view due to the overwhelming brightness of the sun. By studying the corona during eclipses, researchers can gather important information about solar activity, including the behavior of solar radiation and its effects on Earth. One of the most striking features of the corona is its temperature, which can reach millions of degrees, far hotter than the sun's surface. Understanding why the corona is so much hotter than the sun itself is crucial for understanding the dynamics of solar wind and magnetic fields. These factors play a major role in space weather phenomena, which can disrupt satellite communications and even power grids on Earth. As our understanding of solar activity grows, so too does our ability to predict and mitigate the impacts of space weather on our technological infrastructure. Each of these scientific frontiers, from the discovery of phosphine on Venus to the study of solar eclipses, brings us closer to answering some of the most profound questions about our place in the cosmos. Through exploration and research, we continue to gain deeper insights into the workings of our solar system, while also expanding the horizons of what we know about the broader universe. Solar eclipses provide scientists with an invaluable opportunity to refine our understanding of the moon's orbit and its complex relationship with Earth. When the moon crosses in front of the sun, it offers a unique moment to measure its distance from Earth with greater accuracy. These observations help to enhance our models of the gravitational interactions not only between the Earth and the moon, but also with other celestial bodies in the solar system. As a result, scientists gain deeper insights into tidal forces and their effects on our planet, an aspect that is central to both Earth's physical processes and its long-term evolution. More than just a dramatic spectacle, solar eclipses serve as natural laboratories for scientific discovery. They provide crucial moments of clarity, shining a light on the enigmatic outer atmosphere of the sun, the corona, and on the sun's energetic activities. But the significance of these events extends beyond the sun. The moon's intricate movements during an eclipse offer a glimpse into the dynamic relationship between our planet and its satellite, a relationship that influences everything from ocean tides to the stability of Earth's rotation. Each eclipse, brief though it may be, is brimming with potential breakthroughs. It serves as a reminder of the interconnectedness of celestial bodies in our solar system, illustrating how even the most fleeting phenomena can contribute to our expanding knowledge of the universe. Turning our gaze beyond the moon, Mercury, the closest planet to the sun, stands as a mysterious world that continues to challenge our understanding of planetary formation and evolution. This small, rocky planet is an enigma, largely due to its extreme temperature variations and the unique conditions of its surface. Mercury experiences the most severe temperature fluctuations of any planet in the solar system. Daytime temperatures can soar to around 800 degrees Fahrenheit, while nighttime temperatures can plummet to nearly minus 330 degrees Fahrenheit. These extremes are a direct result of Mercury's thin atmosphere, which lacks the ability to retain heat, creating a stark contrast with the more temperate conditions experienced by other planetary neighbors. What makes Mercury truly fascinating, however, is the nature of its surface features. Images captured by NASA's Messenger spacecraft have revealed a landscape deeply scarred by craters, ridges, and colossal cliffs known as lobate scarps. These features suggest that the planet has experienced significant geological activity long after its initial formation. The discovery of these scarps indicates that Mercury's surface has undergone a process of contraction as the planet cooled over billions of years, shrinking in size. This provides a glimpse into Mercury's geological past, preserving evidence of ancient processes that have shaped the solar system as we know it today. As a result, Mercury becomes a key player in deciphering the evolution of the inner planets. Adding to the intrigue is Mercury's magnetic field. Although Mercury is only about a third of Earth's size, its magnetic field is about 1% the strength of Earth's. The origin of this field remains a puzzle for scientists. The presence of a magnetic field suggests that Mercury has a partially molten outer core, which could imply that the planet's interior is still active, despite its small size and proximity to the Sun. This raises important questions about the planet's history and its capacity to sustain such a phenomenon over billions of years. Additionally, Mercury's lack of a substantial atmosphere allows it to be continuously bombarded by solar particles. This constant interaction between Mercury and the solar wind has led to the formation of a surface layer rich in volatile elements such as sodium. This unique feature contributes to Mercury's highly reflective surface, making it one of the most intriguing objects in our solar system. This interaction between a planet and the solar wind has broader implications for understanding the atmospheres and surfaces of other planets, particularly those that are small, rocky, or have weak magnetic fields. Through Mercury, we begin to grasp the diverse ways in which celestial bodies interact with their stellar environments, offering deeper insights into planetary life cycles. Meanwhile, the dwarf planets, particularly Pluto, continue to captivate both scientists and the public. These distant worlds are full of secrets, and their unique status within the solar system only deepens their allure. For many decades, Pluto was considered the 9th planet in our solar system. However, in 2006, it was reclassified as a dwarf planet, sparking a wave of debate and redefining our understanding of what constitutes a planet. This shift forced scientists to reconsider the structure of our solar system and how we categorize celestial bodies, with Pluto and other dwarf planets like Eris and Haumea providing clues about the early solar system and its formation. These dwarf planets are thought to be remnants from the solar system's infancy, preserving essential evidence of the conditions that existed billions of years ago. They are frozen time capsules with surfaces composed of a variety of ices and complex organic molecules. This combination of materials sparks scientific interest, as they may hold vital information about the process that gave rise to planets and potentially life itself. Understanding the surface and composition of these objects can provide insights into the building blocks of life, helping us unravel the potential for life elsewhere in the universe. The exploration of Pluto took a significant leap forward in 2015 with NASA's New Horizons mission. This spacecraft delivered the first close-up images of Pluto, revealing an astonishingly varied surface. Researchers were stunned by the sight of vast plains, towering mountains, and what appeared to be nitrogen glaciers. These findings challenge our preconceived notions about small celestial bodies, suggesting that they can exhibit dynamic geological processes despite their small size and remote location. This includes the possibility of atmospheric activity and even cryovolcanism, where icy materials are ejected from the surface in a manner similar to volcanic eruptions on Earth. These discoveries are not only reshaping our understanding of Pluto and other dwarf planets, but also shedding light on the broader processes that govern the evolution of the solar system. In many ways, the study of these distant worlds, along with the ongoing examination of Mercury and the Moon, allows us to piece together a more comprehensive understanding of the cosmic puzzle. Each new discovery opens up more questions, driving the quest for knowledge in our ever-expanding journey through the universe. Moreover, a growing number of researchers are delving into the fascinating world of dwarf planets and their moons, particularly focusing on the orbital dynamics that govern their motion. One example of this is Pluto's moon, Charon, which has revealed intriguing characteristics that shed light on the nature of binary systems in space. The study of these distant celestial objects has opened a vast array of possibilities for new discoveries, demonstrating just how much remains to be explored. As scientists continue to study these enigmatic worlds, they continually remind us that the universe is an unfathomably complex place, brimming with surprises that spark our curiosity and drive us to explore further. At the heart of the cosmos lies the concept of galaxies, vast collections of stars, gas, dust, and dark matter, all bound together by the force of gravity. These immense structures are the building blocks of the universe, and at the core of many galaxies one can typically find a supermassive black hole, surrounded by hundreds of billions of stars. The arrangement of these stars varies widely, with some galaxies exhibiting sprawling spiral arms, while others take on elliptical or irregular shapes. Our very own Milky Way, for instance, is a striking example of a spiral galaxy, featuring graceful arms that spiral outward, rich with stars and nebulae. The diversity of galaxies in terms of size and shape is truly mind-boggling. The smallest known galaxies, referred to as dwarf galaxies, can contain as few as a few billion stars, while the largest galaxies, known as giant galaxies, can host over 1 trillion stars. Broadly speaking, galaxies can be classified into 3 main categories: spiral, elliptical, and irregular. Each of these classifications reflects distinct features that offer clues to the history and behavior of galaxies. Spiral galaxies, such as the Milky Way, are characterized by a flat disk of stars, gas, and dust, with a bulging central core. The spiral arms, which extend outward from the center, are created by the density of stars and the gravitational forces at play. These arms are typically home to many young, bright stars, lending these galaxies a vibrant, dynamic appearance. In contrast, elliptical galaxies appear more rounded or oval-shaped, with a smooth distribution of older stars. Unlike spiral galaxies, they lack the well-defined arms and disks, and they tend to have much less gas and dust, resulting in a more uniform brightness and color, typically dominated by red hues. This is because the stars in elliptical galaxies are older, having exhausted much of their nuclear fuel, unlike the young, blue stars that shine in spiral galaxies. The formation processes of these galaxies differ significantly as well. Spiral galaxies often continue to form new stars from the gas and dust that spiral inward toward the center. This ongoing activity is maintained by the conservation of angular momentum as matter gets drawn into the galactic disk. On the other hand, elliptical galaxies are typically thought to form as a result of galaxy mergers. When smaller galaxies collide, their stars and gas are redistributed, resulting in a more stable, elliptical shape with little new star formation. Over time, the stars in elliptical galaxies undergo a reshaping of their orbits, contributing to their smooth, uniform appearance. The environments in which these galaxies exist further distinguish them. Spiral galaxies are often found in groups or clusters, where interactions between galaxies are more frequent, and the exchange of material is a regular occurrence. Elliptical galaxies, on the other hand, are more often situated in dense galaxy clusters, where gravitational interactions have shaped their evolution over billions of years. By understanding these differences, scientists can gain critical insights into not just the nature of galaxies themselves, but also the processes that have influenced their formation and evolution over cosmic timescales. Galactic collisions are one of the most captivating phenomena in the universe, representing dramatic and transformative events in the cosmic landscape. When two galaxies collide, the process is far from a simple merging of stars and gas. Instead, it initiates a series of complex interactions that can reshape entire galaxies, redistribute stars, gas, and dust, and even trigger the birth of new stars. These collisions highlight the interconnected nature of galaxies, where each galaxy profoundly influences the others in the encounter, much like dancers performing a cosmic waltz. As the galaxies collide, their mutual gravitational forces create tidal interactions, stretching and pulling at their stellar and gaseous contents, sometimes forming elongated tidal tails filled with newly created stars and stellar debris. This chaotic yet vital process plays a crucial role in the evolution of galaxies. Rather than being destructive, galactic collisions are the drivers of creation, leading to the formation of new stars and even new galaxies. The vast majority of galaxies in the universe have undergone such collisions at some point, and for many such events are still ongoing. One of the most well-known future collisions is the predicted encounter between our Milky Way galaxy and the neighboring Andromeda galaxy, expected to occur in approximately 4 billion years. This cosmic collision will forever alter the structure of both galaxies, likely resulting in a new merged galaxy. In addition to the physical changes caused by these encounters, galactic collisions also provide vital clues about the history and evolution of the universe. By studying the remnants of these collisions, astronomers can trace the paths that galaxies have followed throughout cosmic time, uncovering the story of their formation, growth, and eventual fate. Thus, galactic collisions are not just dramatic events. They are fundamental processes that have shaped the structure of the universe on a grand scale, and they continue to drive its ongoing evolution. Mapping and categorizing the universe's galaxies is one of the most ambitious and challenging projects in modern astronomy. Scientists use powerful telescopes, advanced imaging techniques, and sophisticated data analysis methods to study the distribution and characteristics of galaxies across the cosmos. With an estimated 2 trillion galaxies scattered throughout the universe, each unique in its structure, size, and content, cataloging them is no small feat. It is akin to attempting to map an ocean teeming with stars and other celestial objects, each with its own story to tell. One of the first steps in galaxy mapping involves using both ground-based and space-based telescopes, which can capture light across a wide range of wavelengths from visible light to infrared and beyond. This allows astronomers to observe galaxies as they were billions of years ago, offering a glimpse into their distant past. Large astronomical surveys, such as the Sloan Digital Sky Survey and the Hubble Space Telescope's legacy fields, have gathered vast amounts of data, creating comprehensive catalogs of galaxies that include detailed information about their shape, size, brightness, and color. Once the data is collected, astronomers classify galaxies based on key characteristics, particularly their morphology or structure. The Hubble sequence, for example, divides galaxies into categories, such as ellipticals, spirals, and irregulars. This classification system helps astronomers better understand the processes that drive galaxy formation and how these galaxies interact with their environments. By studying these diverse cosmic structures, we gain a deeper appreciation for the complex forces that govern the universe and the dynamic history of its ongoing evolution. Advances in machine learning have increasingly become a pivotal force in the realm of astronomy, particularly when it comes to processing and analyzing the vast amount of data generated by our observations of the universe. These technological leaps are enabling astronomers to swiftly identify and classify galaxies, an essential task in light of the growing volume of information being collected. Machine learning models trained to recognize patterns in this data now help astronomers stay on top of the overwhelming influx of new data, identifying key structures, anomalies, and changes within galaxies more rapidly than ever before. In addition to examining the galaxies themselves, researchers also focus on their environments, studying galaxy clusters, smaller groups, and the enormous voids that stretch between them. Understanding these contexts can yield crucial insights into the forces shaping the galaxy's behavior, including the influence of gravitational interactions and the invisible presence of dark matter that binds galaxies together. As our observational techniques continue to advance and new, more powerful telescopes come online, the mapping of galaxies has grown more refined and detailed. These breakthroughs are unlocking new perspectives on the universe's cosmic tapestry, shedding light on the intricate and often perplexing way galaxies evolve and interact with one another. Every new discovery helps to further clarify the role these cosmic giants play in the broader narrative of cosmic evolution. At the heart of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole, a cosmic engine of immense power. These black holes are not just objects of theoretical interest. They are central to the structure and function of the galaxies they inhabit. Ranging in mass from millions to billions of times that of our Sun, supermassive black holes exert an enormous gravitational influence on their surroundings. As they grow, they draw in vast quantities of gas, dust, and even entire stars, creating powerful gravitational fields that shape the structure of the galaxy itself. In regions close to the black hole, the gravitational forces can be so intense that they heat up the surrounding material to extreme temperatures, causing it to radiate brightly. This energy output often leads to the formation of an active galactic nucleus, AGN, a region where jets of high-energy radiation and particles are shot out into space, shaping the surrounding interstellar medium. This energetic output from supermassive black holes can have significant effects on star formation within the galaxy. On one hand, the energy they release can stimulate the formation of new stars, creating pockets of intense activity. On the other hand, the expulsion of gas from the galaxy can suppress star formation, leading to periods of dormancy. This delicate balance plays a crucial role in regulating the growth and evolution of galaxies, with the supermassive black hole acting as both a creator and a destroyer of stars. Over billions of years, this dynamic relationship between black holes and their host galaxies shapes the path of their evolution, underscoring the intricate and often unpredictable nature of cosmic development. Supermassive black holes are far more than cosmic vacuum cleaners. They are key players in the story of galactic formation and evolution. They influence not just the structure of their host galaxies, but also their growth, behavior, and interaction with the larger cosmic environment. By delving deeper into the nature of these enigmatic entities, astronomers are beginning to unlock the secrets of galactic formation on an unparalleled scale, expanding our understanding of the universe and our place within it. To better understand how galaxies are structured, astronomers focus on two main components, the halo and the disk. The halo surrounds the galaxy, containing older stars, globular clusters, and a significant amount of dark matter. The disk, which houses the majority of a galaxy's stars and gas, is where the majority of active star formation occurs. To study these components, astronomers use an array of sophisticated observational techniques, each offering unique insights into the galaxy's inner workings. One of the most powerful tools in an astronomer's arsenal is spectroscopy, which allows scientists to break down the light emitted or absorbed by objects in space. By analyzing the spectrum of this light, astronomers can deduce the chemical composition, temperature, and motion of stars and gas within the galaxy. In the disk component, astronomers often examine the distribution and movement of stars, using the rotational velocities of stars at varying distances from the galactic center to uncover key details about the mass and composition of the galaxy. This data also provides crucial clues about the presence of dark matter, an invisible yet influential substance that plays a central role in the galaxy's structure and behavior. Mapping the spiral structure of galaxies can be done with both optical telescopes and radio observatories, which detect cold gas and molecular clouds, key sites where new stars are born. Studying the halo component, however, presents its own set of challenges. The halo is a vast, roughly spherical region surrounding the galaxy, containing the oldest stars, globular clusters, and large amounts of dark matter. To explore this mysterious region, astronomers rely on high-resolution imaging techniques and deep-field surveys. These surveys capture light from distant galaxies, enabling scientists to infer the presence of the halo and its gravitational effects on neighboring galaxies. Additionally, modern telescopes equipped with specialized instruments can detect the faint glow of hot gas and dark matter within the halo. Techniques such as gravitational lensing, where the light from distant objects is bent by the gravity of a massive galaxy, provide valuable insights into the structure and mass of the halo. By combining these observational methods, astronomers are able to create a detailed picture of how the halo and disk components of galaxies contribute to their overall structure. Understanding these intricate components is key to deciphering the larger forces at work in the universe and the complex interplay of matter, energy, and gravity. The birth of new stars within galaxies is a vital indicator of the ongoing processes of cosmic evolution. Stars are the building blocks of galaxies, and their formation is intricately linked to the conditions of the universe at any given moment in time. By studying when and how stars form, scientists can uncover critical insights into the broader history and future of the universe. Stars form in vast clouds of gas and dust, often found in the cold and dark corners of space. When these clouds collapse under their own gravity, they heat up, triggering nuclear fusion at their core, which marks the birth of a new star. The rate of star formation varies significantly from galaxy to galaxy and across different epochs of cosmic history. Factors such as the availability of raw materials, the presence of other nearby galaxies, and external gravitational influences can all impact the rate at which stars are born. By observing these variations, astronomers can construct a timeline of cosmic history, revealing how galaxies have evolved over billions of years and how they may continue to evolve in the future. Star formation is not just a process confined to individual galaxies. It is a key piece of the puzzle in understanding the evolution of the universe itself. Stars are not merely celestial bodies, they are the dynamic engines of cosmic evolution, shaping the universe in ways that continue to unravel mysteries. Massive stars, in particular, play a pivotal role in this process, rapidly evolving and eventually meeting a spectacular end. As they go through their short-lived existence, they release powerful radiation and explosive supernovae that leave a lasting impact on their surroundings. These massive explosions do more than just create dazzling light shows. They enrich the surrounding gas clouds with heavy elements. These elements, such as carbon, oxygen, and iron, are the building blocks for future generations of stars and planets. This cyclical process of stellar birth and death is a cosmic narrative of rebirth, where each new generation of stars carries within it the signature of the conditions that existed at the time of its creation. The birth of a new star offers us a glimpse into the history of the universe, revealing conditions that existed when it first formed. Studying these stars is akin to peering into a time capsule, where each stellar birth is a snapshot of the physical processes that shaped its parent galaxy. This ongoing cycle of creation and destruction helps us understand not only the intricacies of stellar life, but also the broader cosmic evolution. Each generation of stars provides critical clues about how the universe has evolved and how galaxies in particular have been transformed over billions of years. Galaxies themselves are not static. They are constantly evolving, transforming from clouds of gas and dust into magnificent structures of stars. The first phase of a galaxy's life begins when gravity pulls together these particles, sparking the formation of stars. The light from these new stars fills the cosmos, creating a beautiful tapestry of brilliance. Yet, this is only the beginning of a galaxy's journey. Over time, galaxies change in form, size, and composition due to various processes that influence their structure. One of the most significant factors in the evolution of galaxies is the interaction between them. Galaxies are not isolated. They exist in clusters, groups, or sometimes alone in the vastness of space. When galaxies encounter one another, whether through close passes or full-on collisions, the gravitational forces at play can trigger massive waves of star formation. These interactions often reshape the galaxy's structures, potentially leading to the merging of smaller galaxies into a larger, more massive one. In the aftermath of such collisions, the gas and dust from the galaxies are redistributed, fueling the birth of even more stars. These events are responsible for giving rise to some of the most stunning structures in the universe. from majestic spiral galaxies to more compact elliptical forms. The environment in which a galaxy exists also significantly impacts its evolutionary trajectory. In crowded galaxy clusters, interactions are more frequent, leading to a different path of development compared to isolated galaxies. The surrounding material in these environments can influence the rate at which new stars form and the availability of the raw materials needed for stellar creation. Over time, these interactions and environmental influences contribute to the incredible diversity of galaxies that populate the cosmos, each with its own unique shape, size, and stellar population. As galaxies age, their star populations change as well. The life cycle of stars is an ongoing process, with some stars reaching the end of their lives and undergoing dramatic transformations. Some stars explode in supernovae, while others evolve into white dwarfs, neutron stars, or even black holes. These stellar deaths have a profound effect on the galaxy's overall composition, altering the balance of elements and influencing the types of new stars that can form. The story of a galaxy, then, is one of constant flux, shaped by both the interactions between galaxies and the ongoing life and death of stars. Over time, this gives rise to the remarkable variety of galaxies we observe today, each with its own distinctive character. At the heart of the Milky Way, a particularly enigmatic region beckons the attention of astronomers, the galactic center. Located in the direction of the constellation Sagittarius, this area is home to a supermassive black hole known as Sagittarius A star. Despite its invisibility to optical telescopes, the presence of this black hole has been inferred by the behavior of nearby stars. These stars move at astonishing speeds, their orbits revealing the presence of a mass about 4 million times that of our Sun, all concentrated in a space no larger than our solar system. This discovery has raised intriguing questions about the formation and evolution of our galaxy. Yet, despite the progress made in understanding the nature of Sagittarius A, many mysteries remain. One of the biggest puzzles concerns the material swirling around the black hole itself. Is the gas and dust behaving as expected, or are there unseen forces at play? The extreme environment near the black hole generates high-energy radiation, creating a dynamic and chaotic region that challenges our existing theories of particle behavior and gravitational physics. Studying this region offers a rare opportunity to test our understanding of the very fabric of space and time. In the grand scheme of the cosmos, the study of star formation and galactic evolution serves as a window into the deeper workings of the universe. Each new discovery, whether it's a massive star dying in a supernova explosion or the interaction of two galaxies, adds a new layer to our understanding of how the universe has evolved and how it will continue to change. As we observe the stars, galaxies, and black holes that populate our universe, we continue to piece together the extraordinary narrative of cosmic evolution, one that stretches across billions of years and reaches toward the mysteries yet to be uncovered. Moreover, the galactic center is far more than just a haven for black holes and high-energy radiation. It is a thriving epicenter teeming with a rich diversity of stars, vast clouds of gas, and intricate structures known as the nuclear bulge. This hub of intense activity raises profound questions about how stars manage to form and survive in such an extreme environment. How do they withstand the chaotic forces at play? And how do these stellar bodies evolve over time in an area where gravitational forces and radiation are so strong? Studying their life cycles offers vital insights into the broader evolution of the galaxy and could ultimately provide a deeper understanding of our own cosmic neighborhood. Unraveling the mysteries of the Milky Way's center is not just about satisfying our curiosity. It connects to a much larger cosmic picture. These enigmas provide crucial clues about how galaxies evolve as a whole. As scientists refine and expand their observational technologies, such as high-powered radio and infrared telescopes, we may be on the verge of unlocking answers to some of the most perplexing questions that have stumped astronomers for centuries. These technological advancements promise to illuminate the dark heart of our galaxy and potentially unveil new dimensions of the cosmos. In the vastness of the universe, scientists classify galaxies based on their shapes, sizes, and behaviors. Regular galaxies, like spirals and ellipticals, display clear and well-defined structures. Spiral galaxies, for example, feature beautifully curving arms that radiate outward from a bright, densely packed center. On the other hand, elliptical galaxies range from nearly spherical to more elongated, oval-like forms. The striking shapes of these galaxies are the result of millions, even billions of years of gravitational forces working in harmony. These forces sculpt the galaxies into their predictable, steady shapes. However, the peculiar galaxies present a different story. These galaxies defy conventional classifications and are far more enigmatic in nature. They often appear distorted, irregular, or asymmetrical. This unusual appearance can stem from a variety of factors, such as interactions with other galaxies, close encounters with massive cosmic objects, or the explosive forces of supernova. These chaotic events disrupt the normal order of a galaxy's formation, resulting in peculiar shapes that resist easy categorization. As a result, peculiar galaxies stand out as cosmic anomalies, with their unique features prompting further investigation into the forces that drive such unpredictable behaviors. To understand these anomalies, astronomers employ a combination of advanced observational techniques and imaging methods. By analyzing the light emitted by these galaxies, researchers can infer fundamental properties such as their composition, age, and distance from Earth. The key to identifying a peculiar galaxy lies in the subtle irregularities in their structure and behavior. By piecing together these differences, astronomers are able to gain a deeper understanding of the dynamic processes that shape the universe. Peculiar galaxies, with their defiance of order, serve as a reminder of the universe's infinite complexity and unpredictability. They invite scientists to explore the cosmic forces at play, each galaxy telling a unique story about the nature of the cosmos. In the search for extraterrestrial life, the hunt for biosignatures, chemical signs of life, is one of the most exciting and groundbreaking endeavors of modern science. This search begins in our own solar system, where scientists focus on celestial bodies that may harbor conditions suitable for life. Planets and moons, such as Mars, as well as Jupiter's icy moons like Europa and Saturn's Enceladus, are of particular interest. These moons are believed to contain subsurface oceans beneath their icy crusts, making them prime candidates for the existence of microbial life. The quest to explore these extraterrestrial environments is multifaceted, combining robotic space missions, landers, and orbiters. When these missions arrive at their destinations, they are equipped with instruments specifically designed to detect chemical traces of life. These instruments analyze a variety of samples: soil, atmospheric gases, and surface materials for organic compounds, the essential building blocks of life as we know it. For example, NASA's Mars Perseverance rover is on a mission to explore the Martian surface, searching for signs of ancient microbial life by studying soil and atmospheric composition. Scientists have designed these investigations to discern between biological and non-biological processes, ensuring that any potential signs of life are accurately identified. Beyond our own solar system, the search for biosignatures extends to distant exoplanets orbiting far-off stars. Astronomers are using powerful space-based telescopes to study the atmospheres of these planets, looking for specific gases that could point to biological activity. Oxygen and methane are of particular interest, as these gases tend to react with each other. If they are present together in a planet's atmosphere, they could indicate that some form of biological process is actively maintaining these gases, as they would normally break down over time without an ongoing source. Astrobiology, an emerging field at the intersection of multiple scientific disciplines, is helping researchers analyze these findings. By looking for patterns and specific indicators, astrobiologists aim to answer one of humanity's greatest questions: could life exist elsewhere in the universe? While the search is primarily focused on finding life similar to what we know on Earth, it also seeks to understand how life might evolve in different forms and under a range of conditions. This quest for biosignatures, whether through exploring neighboring planets or studying distant exoplanets, fuels our curiosity and deepens our understanding of the potential for life throughout the cosmos. The Fermi paradox, a concept that has puzzled scientists for decades, presents an intriguing contradiction in the search for extraterrestrial life. Despite the universe's vastness, age, and the sheer number of potentially habitable planets, we have yet to find definitive evidence of intelligent life beyond Earth. This paradox, named after the physicist Enrico Fermi, raises critical questions about the likelihood of extraterrestrial civilizations and the reasons for their apparent absence. One compelling theory associated with the Fermi paradox is the Great Filter hypothesis. According to this theory, there may be a crucial near-impossible stage in the evolution of life that most civilizations fail to surpass. While microbial life could be widespread across the universe, the emergence of intelligent civilizations capable of advanced technology and space exploration might be exceedingly rare. This filter could occur at various stages, either before life even emerges on a planet or after civilizations reach a certain technological threshold and face self-destruction through war, environmental collapse, or other catastrophic events. Another theory, known as the zoo hypothesis, suggests that advanced extraterrestrial civilizations might be intentionally avoiding contact with us. This hypothesis posits that these civilizations are observing humanity, much like we observe animals in a zoo. From this perspective, we are still in the early stages of our development, and extraterrestrials may be deliberately refraining from intervening in our natural progression. The vast distances between stars and galaxies, along with the limitations of our current technology, also play a significant role in the silence of the cosmos. The enormity of space makes communication and exploration a monumental challenge. With billions of stars scattered across the universe, the odds of making contact with another civilization are slim, and the difficulties of establishing interstellar communication add yet another layer of complexity to the search for life. As technology advances, however, and our methods for detecting extraterrestrial signals and scanning for biosignatures become more refined, we may uncover that the silence of the universe is not indicative of loneliness, but rather the inherent difficulty of connecting with intelligent beings across such vast distances. Through continued exploration and scientific discovery, we may eventually uncover the answers to the questions posed by the Fermi paradox, opening up new pathways for understanding life's place in the cosmos. Extremophiles, organisms that thrive in environments once thought to be inhospitable, add another fascinating dimension to our search for life beyond Earth. These organisms survive in extreme conditions, from boiling hot springs to the frozen tundra of the Arctic. Their ability to endure such hostile environments challenges our understanding of life's potential limitations and opens up exciting new possibilities for extraterrestrial life. Scientists study extremophiles to learn more about the biochemical processes that allow them to survive in extreme conditions. By understanding how these organisms adapt to stress, we gain valuable insights into what life might look like on other worlds. For example, while Martian soil might not seem capable of supporting life, extremophiles that thrive in high radiation environments could offer clues about how life might endure on Mars. By examining these organisms, scientists are piecing together the puzzle of how life could not only survive, but potentially flourish in the most extreme environments the universe has to offer. Extremophiles, remarkable organisms that thrive in extreme environments, have provided scientists with invaluable insights into the resilience of life. These creatures have been discovered in some of the most inhospitable places on Earth: the frigid, isolated waters of subglacial lakes beneath Antarctica's icy surface, and the intense, boiling depths of deep-sea hydrothermal vents. These environments, harsh by our standards, are remarkably similar to the conditions on distant moons like Europa, which is known to harbor a subsurface ocean beneath its frozen shell. By studying extremophiles and how they adapt to such extreme conditions, researchers are unlocking new clues that can guide the search for life beyond Earth. The survival strategies of these organisms offer a profound perspective on how life could endure on other celestial bodies. Understanding how life forms cope with such hostile settings can lead scientists to identify potential signs of life, known as biosignatures, on far-off planets. These signs could include unique chemical compounds, unusual distributions of elements, or unexpected spatial patterns that hint at life's existence. More than just models of biological resilience, extremophiles are also guiding beacons for the burgeoning field of astrobiology, Their diverse mechanisms for survival challenge our traditional understanding of life's boundaries. The fundamental takeaway from extremophiles is that life is adaptable, far more flexible than we once believed. The universe could very well be teeming with organisms capable of thriving in environments that defy the norms we've long held about habitability. In this light, these earthbound marvels may not only inform our exploration of the universe, but also lead us to groundbreaking discoveries about the potential for life beyond our planet. The search for life in the cosmos is not just fueled by curiosity, it is rooted in scientific frameworks such as the Drake equation. Developed by American astronomer Frank Drake in the early 1960s, this equation was designed to estimate the number of potential civilizations in our galaxy with which humanity might communicate. While it does not offer a definitive answer, the Drake equation sparks critical conversations about the conditions that make intelligent life possible and the factors that influence its emergence in the universe. At its heart, the equation factors in several key variables. These include the rate of star formation in the galaxy, the proportion of those stars that have planets, the number of planets that could potentially support life, and the likelihood that life actually arises on those planets. It also takes into account the probability that life will evolve into intelligent beings, and how long those civilizations can persist and communicate. While the Drake equation offers no simple answers, it challenges us to think critically about the vastness of the cosmos and the conditions that make life possible. The equation's estimates are largely based on the best scientific knowledge available at the time. As we discover more about exoplanets, planets orbiting stars outside our solar system, our understanding of habitability improves, and the estimates produced by the Drake equation may change. This evolving framework speaks to a larger, more profound question. Are we alone in the universe, or is life a common phenomenon spread across the cosmos? The Drake equation fosters not only the search for extraterrestrial intelligence, but also a deeper understanding of life's diversity and humanity's place in the grand expanse of space. With each new technological leap in space exploration, our pursuit to answer the age-old question of whether we are the only intelligent beings in the universe grows ever more sophisticated. Central to this quest is the search for extraterrestrial intelligence, SETI, a groundbreaking initiative dedicated to uncovering any signs of intelligent life beyond Earth. The central philosophy behind SETI rests on the assumption that if technologically advanced civilizations exist elsewhere, they might be sending out detectable signals, such as radio waves, that we could intercept. By systematically scanning the skies with advanced telescopes, SETI researchers aim to identify these signals and ultimately answer the timeless question, are we alone in the cosmos? One of the key advancements in SETI research has been the development of complex algorithms and cutting-edge data analysis techniques. In the past, scientists would painstakingly sift through vast amounts of data collected by radio telescopes, an incredibly labor-intensive process. However, with the advent of artificial intelligence and machine learning, this task has become far more efficient. These technological breakthroughs enable researchers to spot potential signals more quickly and with greater accuracy, significantly increasing the likelihood of detecting genuine extraterrestrial communications. Beyond technological advancements, SETI has also catalyzed a wave of global collaboration, bringing together experts from a wide range of scientific disciplines. Initiatives like the Breakthrough Listen project leverage expertise from astronomy, engineering, and computer science, each contributing a unique perspective to the search for extraterrestrial signals. This interdisciplinary approach not only broadens the scope of research, but also accelerates our understanding of the universe and our place within it. Such collaborations hold the potential to uncover one of humanity's most profound discoveries, the realization that we are not alone in the cosmos, but part of a vast, interconnected community of intelligent life across the stars. Moreover, SETI, Search for Extraterrestrial Intelligence, has expanded its approach far beyond the realm of traditional auditory signals. While radio transmissions remain a key focus, researchers are now investigating a broader spectrum of potential communication methods. Among these, optical signals, specifically lasers, are emerging as promising alternatives. This shift in strategy opens up new avenues for discovering extraterrestrial intelligence. Even if we fail to detect conventional radio waves, the exploration of other forms of transmission, such as laser-based communication, could still lead us to evidence of intelligent life elsewhere in the cosmos. As humanity continues its quest to decipher the vastness of space, each breakthrough in SETI not only propels us forward in our understanding of the universe, but also fuels our collective imagination about what may exist beyond our own planet. The mysteries of space beckon us to question whether we are truly alone in the universe. In this pursuit, recent developments have intensified scientific discussions on the possibility of life on Mars, both past and present. One of the most captivating discoveries to date has been the identification of organic molecules in soil samples collected from the Martian surface by NASA's Curiosity rover. These molecules, which are the essential building blocks of life as we understand it, offer intriguing evidence that Mars may have once harbored the basic components necessary for life. While the presence of these compounds doesn't confirm that life ever existed on Mars, it undeniably raises the tantalizing possibility that the chemical precursors to life could have been present in the planet's distant past. In addition to these organic molecules, scientists have also uncovered seasonal shifts in the Martian landscape that suggest the intermittent presence of liquid water. These findings are crucial, as water is considered a fundamental necessity for life. The fact that water, albeit in highly saline forms, appears to flow on Mars at certain times of the year, points to the intriguing possibility that the conditions on the planet might have once been more conducive to the development of life than we previously thought. This evidence of liquid water, combined with the presence of organic molecules, paints a picture of a world that may have supported life in its early history. One of the most compelling phenomena linked to water on Mars is the occurrence of recurring slope lineae, RSL, dark streaks that appear on Martian slopes during the warmer months. These streaks, which seem to flow down the planet's surface, are widely believed to be connected to the movement of briny liquid water. The discovery of RSL is particularly significant as it suggests that under certain conditions, liquid water may still be active on the Martian surface today. This finding has profound implications for our understanding of Mars' current habitability and its potential to host life in the future. As scientists continue to study these enigmatic streaks, we are inching ever closer to uncovering the secrets of Mars and perhaps confirming that we are not alone in the universe. The search for life beyond Earth has captivated the imaginations of scientists and explorers alike, sparking profound questions about our place in the universe. As our technological prowess advances, so too does our ability to uncover evidence of life that could have existed elsewhere, whether in the past or present. The Martian landscape, for instance, holds secrets that suggest it may once have been more hospitable than it is today. Geologic findings on Mars reveal ancient riverbeds and lake beds scattered across its surface, suggesting that liquid water, a key ingredient for life as we understand it, once flowed there. The presence of clays and other sedimentary rocks further indicates a history shaped by water. These features provide tantalizing evidence that Mars may have supported microbial life long ago, raising the prospect that life could have emerged under conditions similar to those on Earth. Recent Mars missions, including the Perseverance rover, are continuing this exploration with cutting-edge technology designed to unlock the planet's mysteries. Equipped with sophisticated laboratory instruments, Perseverance is not only searching for signs of ancient life, but is also investigating the possibility of life in the planet's current environment. The rover collects and analyzes rock and soil samples with an unprecedented level of detail, helping scientists piece together the planet's history. The missions stand at the forefront of humanity's quest to answer one of the most profound questions of all: are we alone in the universe? As scientists peel back the layers of Mars' history, the prospect of discovering microbial life, whether ancient or active, continues to fuel exploration. Every new discovery on Mars brings us closer to understanding the conditions that allowed life to thrive, if indeed it ever did, on another world. The exploration of Mars has become an inspirational symbol for a new generation of scientists eager to understand more about the origins of life beyond our home planet. Beyond Mars, our gaze turns to distant exoplanets, those worlds orbiting stars outside our solar system. Advances in technology have opened up new frontiers in the study of exoplanet atmospheres, a field that has become crucial in the search for extraterrestrial life. Scientists employ various methods to study these distant worlds, with one of the most important tools being the analysis of light. When a star shines through an exoplanet's atmosphere during a transit event, when the planet passes in front of its star, some of that light is absorbed by the gases in the atmosphere. This creates a unique fingerprint that can reveal the molecular composition of the atmosphere. One of the primary techniques used to decode these atmospheric fingerprints is spectroscopy. By analyzing the spectrum of light that filters through an exoplanet's atmosphere, scientists can identify the gases present, such as water vapor, carbon dioxide, or methane. The presence of certain gases in an exoplanet's atmosphere could suggest conditions that might support life. Of particular interest are gases that, on Earth, are linked to biological processes. For instance, the presence of oxygen or methane could indicate biological activity, raising the possibility that life might exist or once existed on that planet. As instruments like the James Webb Space Telescope continue to evolve, our ability to detect faint signals from distant exoplanets grows stronger. These space telescopes are becoming more sophisticated, allowing scientists to probe deeper into the chemical compositions of distant worlds. With these advanced tools, researchers can look for subtle clues, biosignatures that suggest life may be present or may have once existed in these far-flung realms. Each new mission that expands our understanding of these distant planets brings us closer to understanding whether life exists elsewhere in the universe. In addition to observational data, simulations and models are increasingly used to deepen our understanding of exoplanet atmospheres. By comparing real-world data with theoretical predictions, researchers are refining their approaches, enhancing our knowledge of the conditions under which life could arise. This dynamic interaction between observation, analysis, and simulation creates a vibrant synergy, driving the quest for extraterrestrial life forward. Each clue from an exoplanet brings us closer to answering one of humanity's most profound questions. Are we alone in the universe? Astrobiology missions play a pivotal role in this quest, blending biology, chemistry, geology, and astronomy to explore the potential for life across the cosmos. These missions focus on identifying the building blocks of life and studying the conditions under which life can thrive. By examining environments in our solar system and beyond, astrobiologists can form hypotheses about where to look for life and what it might look like. One major focus is the exploration of planets and moons within our own solar system. Mars, for example, is a prime target for astrobiologists. The Perseverance rover is actively investigating the planet's geology and climate, searching not just for evidence of past life, but also gathering crucial data about its history of water, essential for life as we know it. Similarly, the icy moons of Jupiter and Saturn, such as Europa and Enceladus, have garnered significant attention due to the subsurface oceans beneath their frozen crusts. These hidden oceans could provide the ideal conditions for microbial life to exist. As missions to these moons continue, scientists are gaining insights into the potential habitability of these distant worlds. However, astrobiology isn't limited to our solar system. The study of exoplanets, especially those in the so-called habitable zone of their stars, is rapidly advancing. Instruments like the James Webb Space Telescope are designed to analyze the atmospheres of these planets, searching for chemical markers or biosignatures that could point to the presence of life. Detecting gases like oxygen or methane could signal biological processes, prompting further investigation into whether life exists on these distant worlds. Ultimately, astrobiology missions serve as a crucial tool in answering one of humanity's most profound questions. Are we alone in the universe? Each mission brings us closer to understanding the resilience and diversity of life, not just on Earth, but across the cosmos. These endeavors fuel our curiosity and provide a roadmap for the ongoing search for life among the stars. While the search for biological life is at the heart of astrobiology, another avenue of exploration focuses on the search for technosignatures. Technosignatures are indicators of advanced extraterrestrial civilizations. artifacts, signals, or even megastructures that suggest the presence of intelligent beings capable of manipulating energy and resources on a grand scale. Unlike the biological search, which seeks signs of life through chemical markers and biological processes, the search for technosignatures is more focused on identifying evidence of technological activity. This search can take many forms, from detecting radio waves or laser pulses to identifying physical structures that might alter the celestial environment around them. The fundamental difference lies in the concept of intelligence. Whereas biological searches aim to identify life, the search for technosignatures aims to find evidence of technological civilizations. This could involve anything from analyzing star systems for potential artificial structures to listening for signals from distant planets. Each approach adds a new dimension to our understanding of the universe. While the biological search often draws on disciplines like chemistry and biology, the hunt for technosignatures is rooted in astrophysics and engineering. Together, these efforts form a complementary search for life and intelligence in the cosmos, offering new perspectives on the potential of extraterrestrial civilizations and life forms. Finally, the discovery of extraterrestrial life, whether microbial or intelligent, raises profound ethical questions. Should we interact with these newfound beings, and if so, how? Would they deserve the same respect and protection as life on Earth? The discovery of extraterrestrial life challenges us to rethink our ethical frameworks, asking whether we would extend rights and protection to these beings, no matter their level of intelligence or complexity. As we continue to push the boundaries of exploration and discovery, these ethical considerations will remain at the forefront of the conversation, shaping how humanity approaches its place in the broader universe. Imagine the profound implications of a discovery that forever alters our understanding of existence itself, the revelation that we are not alone in the universe. Such a monumental shift would undoubtedly shake the very foundation of human beliefs, relationships, and cultural narratives. For centuries, humanity has looked to the stars with a sense of wonder, pondering the possibility of extraterrestrial life. Yet, the moment we discover it, everything we thought we knew about our place in the cosmos could unravel. The impact on religion, philosophy, and politics could be staggering. Long-held religious doctrines might be called into question, leading to profound shifts in how we view humanity's role in the universe. In the realm of philosophy, the discovery could spark a reevaluation of our concepts of consciousness, life, and even the meaning of existence. Politically, it might reshape national and global priorities as governments grapple with the potential consequences of such a revelation. However, the human response to such an extraordinary discovery is unpredictable. Some may react with fear, others with excitement, and some with skepticism. The diverse range of reactions speaks to the complexities of the human psyche and our struggle to comprehend the unknown. One of the most pressing ethical concerns would be the timing and manner in which this information is disclosed. Would it be appropriate to make such a discovery public immediately, or should it be kept secret until the world is better prepared to handle the news? Furthermore, if these extraterrestrial beings possess intelligence, humanity would face a dilemma about how to engage with them. Should we seek to communicate, collaborate, or perhaps even intervene in their affairs? The ethical implications would be profound, especially in light of the history of our own planet, where encounters between different cultures have often led to the exploitation and domination of one group by another. Should we strive to establish peaceful relationships, or would it be more respectful and ethical to leave them undisturbed, allowing them to develop on their own terms? These questions not only raise important ethical considerations, but also force us to reflect on our own values as a species. In the face of such a discovery, we would be called to consider the responsibilities that come with new knowledge. Our exploration of the cosmos would also prompt us to reconsider our environmental ethics. Would the desire to explore or exploit other worlds divert our attention from the urgent need to protect and preserve our own planet? In grappling with these ethical dilemmas, we are not only preparing for the possibility of extraterrestrial contact, but also learning more about our own priorities, values, and the type of future we hope to create. The universe is vast and mysterious, filled with phenomena that challenge our understanding of the fundamental processes that govern existence. One of the most enigmatic of these phenomena is the gamma-ray burst, a cosmic event so powerful that it releases energy equivalent to that of billions of suns exploding simultaneously. These flashes of gamma radiation, though brief in duration, offer astronomers a unique window into the workings of the universe, providing crucial insights into the birth and death of stars, the formation of galaxies, and the very nature of space and time. Gamma-ray bursts occur in the aftermath of cataclysmic events, such as the collapse of massive stars into black holes or the merger of neutron stars. When such an event takes place, the burst releases an immense amount of energy, often outshining entire galaxies. This energy travels vast distances across the cosmos, allowing astronomers to study these bursts from billions of light years away. In doing so, they gain a glimpse into the state of the universe shortly after the Big Bang, shedding light on its early evolution. Beyond their significance in understanding the universe's origins, gamma-ray bursts also play a crucial role in the study of stellar life cycles. When massive stars die, they often end in spectacular explosions, enriching the cosmos with heavy elements that are essential for the formation of planets and, ultimately, life as we know it. By studying gamma-ray bursts, scientists gain insights into the processes that lead to the death of stars, and in doing so, uncover the intricate relationships between stellar deaths and the development of complex cosmic structures. Gamma-ray bursts also offer tantalizing clues about some of the most elusive mysteries of the universe, such as dark matter and dark energy. The extreme environments in which these bursts occur may hold the key to understanding the fundamental forces that shape the cosmos. Scientists are eager to unravel the mysteries of gamma-ray bursts, as they promise to unlock crucial information about the very fabric of the universe and its evolution. In a similar vein, fast radio bursts, FRBs, have captivated astronomers since their discovery in the early 21st century. These brief and intense bursts of radio waves, lasting just milliseconds, can release as much energy as the sun does in several days. Their sheer intensity and transient nature make them fascinating objects of study, yet their origins and mechanisms remain largely unsolved. What makes FRBs particularly intriguing is their rarity. While these bursts can be detected by radio telescopes, the vastness of the universe means that spotting them is a challenge akin to finding a needle in a cosmic haystack. Only a handful of these bursts have been mapped out, and scientists are still grappling with the task of pinpointing their sources across the billions of galaxies that populate the cosmos. Adding to the mystery is the uncertainty surrounding whether these bursts are isolated events or part of a repeating pattern. Each new discovery opens the door to a range of potential explanations, from highly magnetized neutron stars known as magnetars to cataclysmic events like supernovae, or even massive energy releases from distant galaxies. Yet despite these various hypotheses, the lack of definitive evidence means that the true nature of FRBs remains elusive, continuing to perplex and intrigue scientists around the world. The search for answers continues as astronomers and physicists work tirelessly to unravel the secrets of these enigmatic phenomena. In doing so, they hope to gain a deeper understanding of the forces that govern the universe and our place within it. Whether through gamma-ray bursts or fast radio bursts, these cosmic events offer us a glimpse into the unknown, urging us to look deeper into the mysteries of the universe and perhaps one day understand the very nature of reality itself. The impact of fast radio bursts, FRBs, is expanding rapidly, capturing the attention of researchers who are detecting repeating signals that suggest these bursts may be far more complex than initially believed. This discovery raises an array of questions about their origin, purpose, and what they can reveal about the evolution of the universe itself. As technology advances and further research is conducted, scientists are hopeful that the secrets behind these intense bursts of energy will soon be decoded. The study of FRBs may hold the key to uncovering new realms of cosmic physics and could reshape our understanding of the universe. Indeed, the journey to comprehend the true nature of fast radio bursts remains one of the most thrilling and promising frontiers in modern astronomy. Meanwhile, in the polar regions, auroras, those Those mesmerizing natural light displays are far more than just a breathtaking spectacle. They serve as windows into the intricate interactions between a planet's magnetic field and the solar wind. When charged particles emitted by the sun collide with a planet's atmosphere, they are funneled toward the poles by the planet's magnetic field lines. This interaction generates striking visual effects, as the particles excite molecules of oxygen and nitrogen in the atmosphere, causing them to emit vibrant colors that ripple and dance across the sky. The study of these auroras provides scientists with invaluable insights into the strength and structure of a planet's magnetic field. The intensity and patterns of auroras can reveal crucial details about how a magnetic field defends a planet from solar radiation. For Earth, our magnetic field acts as a protective shield, diverting harmful solar winds and preventing them from stripping away the atmosphere. Moreover, variations in auroral activity can signal changes in both solar output and the geomagnetic conditions in space. By analyzing these dynamic patterns, researchers can deepen their understanding of Earth's magnetic shield, comparing it with the magnetic fields of other planets. The study of auroras also opens up a unique opportunity to explore the solar interactions of other celestial bodies. For example, researchers have documented spectacular auroras on both Jupiter and Saturn. These displays are not only visually captivating, but also feature far more intense storms than those seen on Earth. These observations suggest that planets with strong magnetic fields and fast-moving solar winds experience much more violent auroral displays. As a result, scientists can infer the strength of these planets' magnetic fields and gain insight into their atmospheric compositions. Ultimately, auroras serve as a cosmic signaling system, offering vital information about how a planet interacts with solar energy. By examining these dazzling phenomena, scientists continue to unlock the mysteries of our solar system. Their study enhances our understanding of magnetic fields, atmospheric processes, and the broader implications for planetary habitability. The sun's most dramatic phenomena, solar flares and coronal mass ejections, CMEs, are powerful events that can send shock waves through our solar system, causing a range of impacts. A solar flare is a sudden eruption of energy on the sun's surface, releasing intense bursts of radiation across the electromagnetic spectrum. These powerful emissions can disrupt communication systems on Earth and pose a significant threat to astronauts in space. Coronal mass ejections, often referred to as CMEs, are even more massive and expansive than solar flares. These colossal clouds of charged particles expelled from the sun travel through space at incredible speeds, sometimes exceeding 1,000,000 miles per hour. When a CME reaches Earth, it can cause geomagnetic storms by interacting with our planet's magnetic field. While these storms can produce awe-inspiring auroras in the polar regions, they can also cause widespread disruptions. Power grids can be knocked offline, and satellite operations can be severely impacted, illustrating the tight interconnection between our technology and cosmic events. Solar activity extends beyond Earth, however, affecting other planets in the solar system, especially those with thinner atmospheres like Mars. CMEs have been blamed for stripping away the atmosphere of these planets, drastically altering their environments over millions of years. This phenomenon is of particular concern for future human exploration on Mars, where understanding solar activity is critical to protecting equipment and any potential colonists. Solar flares and CMEs serve as powerful reminders of the sun's profound influence over the solar system. These events shape space weather, and their study is essential for understanding the complex dynamics between solar forces and planetary systems. By continuing to monitor these phenomena, scientists can better predict their effects, which in turn helps protect our technology and supports humanity's ongoing exploration of the cosmos. Cosmic voids, vast regions of space that contain few or no galaxies, are some of the most enigmatic structures in the universe. These voids, which can stretch for tens of millions of light years, occupy a significant portion of the universe's volume, accounting for roughly 80% of it. Imagine the universe as a sponge. The dense regions are filled with galaxies and galaxy clusters, while the larger, more open spaces represent these cosmic voids. The existence of these vast emptinesses is far from trivial. They are fundamental to understanding the universe's architecture. Their presence challenges long-standing theories about the distribution of matter in space. For much of history, scientists believed that matter was evenly spread across the universe. However, the discovery of these massive voids suggests a far more complex and uneven cosmic structure. The existence of these vast empty regions raises critical questions about the processes governing galaxy formation and evolution. Why are certain areas of space so sparsely populated? What forces contribute to the creation and expansion of these voids? These questions continue to intrigue astrophysicists, forcing them to rethink long-held assumptions about how the universe is organized. Cosmic voids are not just empty spaces. They are crucial to understanding the large-scale structure of the universe and the forces at play in shaping it. As research into these vast voids continues, scientists are gaining a deeper appreciation for the complexity and mystery of the cosmos, helping to uncover the true nature of the universe's architecture. Cosmic voids are not just empty stretches of nothingness, but rather, they hold key insights into the very fabric of our universe. These vast, seemingly hollow regions are expanding as the universe itself grows. In denser parts of the cosmos, galaxies continue to cluster together, while the voids between them seem to grow larger. By studying the dynamics of these vast empty spaces, scientists can gain crucial knowledge about the rate of the universe's expansion. Interestingly, the behavior of voids suggests that not all areas of the universe respond the same way to dark energy. This observation is a pivotal piece of the puzzle in our ongoing quest to understand the cosmos. Dark energy, which is believed to drive the accelerated expansion of the universe, appears to have varying effects in different regions. By examining this discrepancy, researchers can refine our understanding of the force that is driving the universe to expand at an ever-increasing rate. Voids have a far-reaching influence, even extending to the cosmic microwave background, CMB radiation, which is the afterglow of the Big Bang. These massive regions of emptiness affect the CMB by subtly distorting the radiation patterns through gravitational effects. Such distortions offer cosmologists a valuable tool for investigating the origins of the universe. While cosmic voids may seem to be empty, they are far from insignificant. They reveal profound truths about the nature of space, time, and the universe's grand design. Far from being mere nothingness, these voids challenge our understanding and continue to shape the way we perceive the universe's vastness. Gravitational lensing is another awe-inspiring phenomenon that helps scientists uncover the mysteries of the universe. When light from a distant object, such as a galaxy or quasar, passes by a massive foreground object like another galaxy or a galaxy cluster, the light is bent due to the curvature of space-time. This bending of light is a direct consequence of Einstein's general theory of relativity, which demonstrates how mass can warp the fabric of space-time. Astronomers have harnessed this natural cosmic lens to peer deeper into the universe, revealing objects that would otherwise be hidden from view. When gravitational lensing occurs, the light from distant sources is distorted into arcs, multiple images, or even complete ring structures. These distortions provide valuable clues about the mass and distribution of the foreground object causing the bending. Using intricate mathematical models, astronomers can reconstruct the three-dimensional structure of the lensing mass, shedding light on the unseen distribution of dark matter, an invisible yet gravitationally influential component of the universe. In addition to mapping dark matter, gravitational lensing is instrumental in measuring the universe's expansion. By studying the light from galaxies that have been bent by gravitational lensing, scientists can track how light travels over vast cosmic distances. This allows them to measure the expansion rate of the universe more accurately, refining essential cosmological parameters, including the Hubble constant. Far more than a visual phenomenon, gravitational lensing is a critical observational tool in modern astrophysics. Through it, astronomers can peer into the invisible realms of dark matter, explore the dynamics of galaxy formation, and gain deeper insights into the very nature of the universe. Each new observation provides us with a more detailed picture of the cosmic web, revealing the hidden forces shaping the universe's structure. Cosmic rays are another intriguing and high-energy aspect of our universe, offering a glimpse into some of the most violent and energetic processes occurring in space. These particles, mostly protons, travel through the cosmos at nearly the speed of light. When they collide with atoms in Earth's atmosphere, they create showers of secondary particles that can be detected. The origins of cosmic rays are traced back to some of the most extreme environments in the universe, including supernova explosions, neutron stars, and active galactic nuclei. One of the greatest mysteries surrounding cosmic rays is how they acquire their enormous energy. Scientists believe that shock waves from supernovae or magnetic fields surrounding neutron stars may contribute to the acceleration of these particles. These environments are capable of converting kinetic energy into far more powerful forms, making cosmic rays among the most energetic particles in the universe. As researchers continue to study cosmic rays, they uncover more about the extreme conditions and processes happening in these violent environments. But the study of cosmic rays doesn't stop at the particles themselves. These rays also offer a window into understanding dark matter and dark energy. While some of the particles appear to originate from known sources, others seem to travel vast distances, possibly influenced by regions of space dense with dark matter. By studying these rays, scientists can gain indirect evidence that may help unravel the nature of these mysterious cosmic components. The study of cosmic rays is thus not just about understanding the particles themselves, but also about exploring the extraordinary events that generate them. Each cosmic ray serves as a clue, a tiny fragment of knowledge that may eventually lead us to a greater understanding of the universe's most energetic processes. With each new discovery, cosmic rays may help uncover more mysteries of the cosmos, further enriching our understanding of space, time, and the nature of the universe itself. The solar wind, a continuous flow of charged particles primarily composed of protons and electrons, is another crucial element in shaping space weather and the environments of various planets within our solar system. Traveling across space at speeds of up to 1 million miles per hour, this stream of particles carries with it the sun's magnetic field, interacting with planetary atmospheres, magnetic fields, and bodies in space. For planets like Earth, which possess magnetic fields, the solar wind is largely deflected, forming a protective barrier that shields the planet from the harmful effects of these charged particles. This magnetic shield is essential for maintaining the integrity of Earth's atmosphere, preventing the solar wind from stripping it away over time. The solar wind's impact extends beyond Earth, affecting other planets, moons, and even the comets and asteroids within the solar system. By studying the solar wind, scientists can gain insights into how these interactions shape the conditions on different celestial bodies and how space weather influences the solar system as a whole. Through this ongoing research, we continue to deepen our understanding of how the sun's continuous outpouring of energy and particles shapes the very environment in which we live. Each of these cosmic phenomena, from voids and gravitational lensing to cosmic rays and the solar wind, contributes a unique piece to the ever-expanding puzzle of the universe. Together, they help us understand the universe's origins, its ongoing evolution, and the unseen forces that govern its behavior. Through these studies, we are continuously uncovering new layers of knowledge about the universe, knowledge that challenges our perceptions, fuels our curiosity, and drives us to explore the vast, mysterious expanse of space. When the intensity of the solar wind increases, particularly during events such as solar flares or coronal mass ejections, it can lead to significant disruptions. These intense bursts of solar activity can cause geomagnetic storms, which have the potential to interfere with a wide range of technological systems on Earth. Satellites may experience malfunctions, navigation systems can be thrown off course, and power grids might face major outages. This highlights the delicate balance between celestial forces and human technology. On planets that lack a strong magnetic field, like Mars, the effects of the solar wind are even more dramatic. Mars, for example, has been stripped of much of its atmosphere over billions of years because it does not have a protective magnetic shield. The relentless bombardment from the solar wind has caused water vapor and other volatile elements to escape into space, severely impacting the planet's climate and surface conditions. Understanding this process is crucial for understanding not only the present state of planetary environments, but also their historical evolution. The influence of the solar wind extends far beyond Earth. It plays a defining role in the heliosphere, the vast region surrounding the Sun, which is dominated by the Sun's magnetic influence. In this cosmic expanse, the solar wind interacts with the interstellar medium, creating a range of complex astrophysical phenomena. These interactions give rise to vibrant auroras seen in the polar regions of various planets, as well as to the breathtaking cosmic landscapes observable throughout our galaxy. Thus, the solar wind is far more than a mere byproduct of solar activity. It is a dynamic and constant force that continuously shapes the environment of our solar system. Beyond the immediate effects on planets like Earth, it molds the very structure of space itself, influencing the way matter behaves throughout the cosmos. In the vastness of the universe, superclusters are among the most impressive structures, representing some of the largest formations known to exist. These superclusters are immense collections of galaxies, interconnected in ways that form vast networks spanning hundreds of millions of light years. To put that in perspective, the size of a supercluster often exceeds the comprehension of human scale, its breadth so vast that it challenges the limits of our observational tools. A supercluster might consist of hundreds or even thousands of galaxies, each bound together by the gravitational forces that govern the cosmos. These colossal formations play a crucial role in shaping the large-scale structure of the universe, organizing the cosmic web of matter. Their presence is not random, but rather a reflection of the underlying gravitational forces that shape the universe itself. Gravity pulls matter into concentrated regions, leading to the formation of these galaxy clusters. As superclusters evolve, they create deep gravitational wells, areas of intense gravity that not only hold the galaxies together, but also influence the surrounding cosmic landscape. This clustering of matter forms a web-like structure across the universe, filled with vast voids and dense filaments. Galaxies and clusters of galaxies are arranged along these highways of dark matter, revealing a cosmic tapestry of immense scale. Understanding superclusters gives scientists essential insight into how matter and energy are distributed across the universe, offering clues about its composition and ultimate fate. Superclusters are not evenly distributed across space. Observations show that they tend to cluster more densely in certain regions, providing valuable information about the distribution of matter in the universe. For instance, by studying the movement and interactions of galaxies within these superclusters, researchers can glean clues about dark energy, the mysterious force believed to be driving the accelerated expansion of the universe. Beyond this, superclusters also have a profound impact on the formation of new stars and the evolution of galaxies. The gravitational influence of one galaxy on another can lead to interactions and even mergers, transforming the characteristics of the galaxies involved. As scientists continue to explore the dynamics of these superclusters, they uncover complex interactions that govern the cosmic environment. Through these studies, we are not only learning more about the past history of the universe, but we are also gaining valuable insights into its future trajectory. To better understand the intricate processes that govern the universe, scientists use a variety of methods. One of the most powerful tools in their arsenal is computer modeling, which allows researchers to simulate cosmic events and phenomena. By creating detailed and sophisticated simulations, scientists can replicate conditions such as the formation of galaxies, the behavior of black holes, or the dynamics of cosmic collisions. These models account for numerous variables and physical laws, giving scientists a way to visualize scenarios that would otherwise be impossible to observe directly. In addition to computer simulations, scientists also rely on numerical simulations that require immense computing power. These simulations enable researchers to analyze vast amounts of data about cosmic phenomena. For example, astrophysicists use supercomputers to model the evolution of the universe, studying how matter clusters and interacts over billions of years. These simulations allow us to trace everything from the Big Bang to the complex structures of galaxies, galaxy clusters, and dark matter that populate our observable universe today. In some cases, scientists recreate cosmic events in controlled laboratory settings, such as in high-energy particle colliders. Facilities like the Large Hadron Collider, LHC, allow researchers to simulate the extreme conditions of the early universe shortly after the Big Bang. By replicating the high-energy environments of the early cosmos, these experiments provide crucial insights into the behavior of fundamental particles and forces. Through these controlled settings, scientists are able to observe how matter behaves under extreme conditions, shedding light on the processes that occur throughout the universe and helping us understand the very building blocks of reality itself. Observational astronomy plays a crucial role in complementing the simulations that scientists use to understand the vast cosmos. By studying celestial phenomena like the aftermath of supernova explosions or the merging of neutron stars, astronomers are able to validate their theoretical models with real-world observations. This synergy between simulation, experimentation, and observation creates a comprehensive framework that continuously enhances our understanding of cosmic events. It allows scientists to refine their knowledge of the universe's intricate workings, gradually piecing together the enormous puzzle of the cosmos. This approach to knowledge extends beyond our immediate universe and touches on the profound and often mind-bending concept of the multiverse theory. At its core, the theory suggests that our universe is but one of many, perhaps even an infinite number of universes existing simultaneously. In this framework, each universe could possess distinct physical laws, constants, and dimensions, all of which might differ vastly from our own. The multiverse challenges the conventional view of reality, which has long focused on a singular universe that emerged from the Big Bang. Instead, it opens the door to imagining a vast, interconnected web of universes, each with its own unique set of properties. Several scientific hypotheses form the backbone of the multiverse theory. One of the most prominent is rooted in the realm of quantum mechanics. In particular, the idea of quantum superposition suggests that every possible outcome of a quantum event occurs in its own distinct universe. Essentially, when a quantum decision is made, whether in a particle's behavior or in the very fabric of reality itself, each potential outcome occurs in a separate, parallel universe. This implies that countless versions of reality could exist, all branching out from different decisions at the quantum level. Another key foundation of the multiverse theory comes from cosmology, specifically inflation theory. This theory postulates that shortly after the Big Bang, the universe experienced a rapid, exponential expansion. This expansion could have generated bubbles, each representing an independent universe, all with their own specific characteristics. This scenario paints a picture of an ever-expanding cosmic landscape, one where new universes continually emerge and diverge, each shaped by its own unique conditions. The implications of the multiverse theory are vast, reaching far beyond our current understanding of reality. If multiple universes do exist, questions arise about the nature of existence itself. Could other forms of life exist in universes with entirely different laws of physics? Could these universes intersect or even influence one another? While the theory remains controversial and is still the subject of intense scientific debate, it undeniably challenges our conceptions of the cosmos in profound ways, pushing the boundaries of human knowledge and imagination. Parallel universe theory, often referred to as the multiverse theory, has emerged not only as a topic of serious scientific investigation, but also as a captivating subject within popular culture. At the heart of this theory lies the notion that multiple universes exist alongside our own, each potentially governed by different physical laws or containing alternate versions of ourselves. These parallel universes may diverge from key moments in history, creating alternate realities that branch off from decisions made at critical junctures. In the scientific realm, parallel universe theory presents profound challenges to our understanding of reality. It forces physicists to consider scenarios that stretch beyond the limits of our observable universe. For instance, the idea that every decision we make could create a new universe, each with a different outcome, has led to new ways of thinking about the fundamental nature of time, space, and existence. In these new frameworks, time is no longer a linear progression. Instead, it becomes a vast network of potential realities, each unfolding in its own direction. The implications of this theory extend far beyond the confines of science. Popular culture has enthusiastically embraced the idea of parallel universes, integrating it into stories across films, television shows, and literature. These narratives explore the concept of alternate realities, offering new perspectives on identity, choice, and destiny. Shows like Doctor Who and movies like Spider-Man Into the Spider-Verse captivate audiences by exploring the idea of parallel worlds and alternate versions of familiar characters. These stories invite viewers to question the nature of reality, giving them a new lens through which to ponder deep philosophical and existential questions. This intersection of science and popular culture enriches both fields. While scientific exploration pushes the boundaries of human knowledge, the creative realm of storytelling allows for a playful engagement with these complex concepts, making them more accessible and relatable to a broader audience. Whether through rigorous scientific research or imaginative fiction, the allure of the multiverse encourages us to contemplate possibilities that stretch the very limits of what we know about our universe and our place within it. Wormholes, another fascinating concept rooted in theoretical physics, further amplify the intrigue surrounding the mysteries of space and time. These hypothetical passages through space-time could serve as shortcuts connecting distant points in the universe, and perhaps even different moments in time. Imagine a tunnel-like structure that links two regions of space-time, creating an almost instantaneous route between them. The concept originated from Einstein's equations of general relativity, which suggest that space-time itself is flexible, capable of bending and stretching under certain conditions. Wormholes, if they exist, could represent a bridge between separate regions of space, allowing for a more efficient traversal of the cosmos. What makes wormholes particularly intriguing is their potential for time travel. If a wormhole could be manipulated by moving one end at relativistic speeds, for example, or placing it in a strong gravitational field, time could pass differently at each end. This phenomenon, known as time dilation, would create a situation where a traveler entering one end of the wormhole could emerge in a different time period, having effectively moved through both space and time within moments. This concept, while popular in science fiction, raises profound questions about the nature of time and reality itself. However, the theoretical nature of wormholes comes with significant challenges. One of the primary obstacles is ensuring the stability of these structures. Most current theories suggest that a wormhole would require a form of exotic matter with negative energy density to remain open. This exotic matter, which would counteract the gravitational forces trying to collapse the wormhole, has not yet been discovered, and its existence remains purely speculative. While the idea of wormholes continues to captivate the imagination of both scientists and science fiction enthusiasts alike, the practical realities of their existence are still very much unknown. These concepts, observational astronomy, the multiverse, parallel universes, and wormholes, are not just theoretical musings. They represent the cutting-edge frontiers of scientific inquiry and offer a lens through which we can expand our understanding of the universe. From the birth of stars to the possibility of infinite universes, these ideas challenge our notions of space, time, and reality. They invite us to envision a universe far grander and more complex than we could have ever imagined, urging us to keep exploring the unknown. Furthermore, even if wormholes did exist, they would raise a multitude of intricate questions, especially concerning causality and the potential paradoxes of altering history. The idea of altering the past is a concept that would significantly complicate the very notion of time travel. At the core of these dilemmas is the possibility of creating events that loop back on themselves, creating paradoxes that defy our conventional understanding of cause and effect. This makes the exploration of wormholes a complex and controversial topic, and one that challenges the very foundations of how we perceive time itself. Despite these hurdles, the study of wormholes and their potential consequences continues to fascinate both scientists and theorists. They stand as a profound reminder of the vast unknowns that exist at the very edge of our understanding of the cosmos. As researchers delve deeper into the realms of quantum physics and general relativity, the tantalizing possibility of wormholes presents the potential for new breakthroughs, perhaps even unraveling long-held mysteries about the nature of space, time, and reality. There is always the hope that one day, through continued exploration, we may uncover truths about the universe that were once thought impossible to grasp. One of the most fascinating and thought-provoking concepts to arise in modern physics is the holographic principle, an idea that suggests the entire universe could be encoded as information on a distant surface or boundary, rather than being a reality that exists independently in 3 dimensions. To illustrate this, imagine the cosmos as a 3-dimensional hologram, where everything we perceive as reality is merely a projection of information stored in a lower dimensional format. This idea is revolutionary, as it challenges our current understanding of space and time, urging us to rethink the fundamental nature of reality itself. If this principle holds true, it could unite the realms of quantum physics and gravity, offering profound insights into the mysteries of black holes, the nature of space-time, and perhaps the most elusive forces in the universe. Traditional physics has long treated space and time as separate, independent entities. But the holographic principle pushes us to reconsider this distinction, suggesting that rather than being separate, these dimensions might arise from a deeper, more fundamental interaction of information. This radically shifts our perspective and opens the door to the possibility of theories that connect the microcosm, the subatomic particles that govern the smallest scales of existence, with the macrocosm, the vast expanses of the universe. Such a paradigm shift could change the way we think about the connections between everything in the universe, perhaps even unraveling the deep interrelations between the structure of the universe and the fundamental forces that govern it. Moreover, the holographic principle could offer new insights into human consciousness and perception. If our reality is indeed a projection, the way we experience the world could be a reflection of deeper, non-physical information that lies beneath the surface of our observable universe. This connection between information and consciousness could lead to groundbreaking discoveries about the nature of human perception, consciousness, and the very limits of what we can know about the universe. The possibility that the universe functions more like an immense computer code than a tangible, concrete structure could change the way we understand not just the cosmos, but our very place within it. The implications of the holographic principle extend far beyond the confines of theoretical physics. This idea has the potential to reshape discussions in philosophy, consciousness studies, and even spirituality. By suggesting that our perceived reality is simply a projection of encoded information, it invites profound questions about existence, purpose, and our relationship to the cosmos. If we are indeed living in a holographic reality, gaining a deeper understanding of this principle could revolutionize not only the field of science, but also the very way we perceive and interpret our existence in the universe. It could challenge everything we thought we knew about the fabric of reality itself. Quantum foam is another compelling concept in theoretical physics, offering a glimpse into the deepest structure of the universe. Proposed to exist at the Planck scale, which is about 100 billion times smaller than an atom, quantum foam describes the turbulent, frothy structure of space-time at the smallest imaginable scales. At this level, the smoothness of space-time that we typically experience breaks down, giving way to a chaotic, frothy essence that resembles bubbles in a foamy liquid. This quantum foam is a manifestation of the constant fluctuations of energy and particles, where particles and waves can appear and disappear in an instant, an inherent feature of the quantum world. The significance of quantum foam lies in its potential to unlock our understanding of gravity and the fundamental forces of nature. Einstein's theory of general relativity treats space-time as a smooth, continuous fabric, but quantum foam suggests that at the smallest scales, this smoothness gives way to a more complex and erratic structure. This raises the possibility that space-time at these levels is far more dynamic than we ever realized, with fluctuations that could offer crucial insights into the workings of gravity within the quantum realm. This remains one of the great puzzles in modern physics, as we currently lack a unified theory that can seamlessly integrate gravity with the principles of quantum mechanics. The discovery of quantum foam could provide the key to solving this long-standing issue, perhaps offering a bridge between the macroscopic laws that govern the large-scale universe and the microscopic forces that dominate at the subatomic level. Through the continued study of these concepts, wormholes, the holographic principle, and quantum foam, scientists and theorists are inching closer to a deeper, more unified understanding of the universe. These ideas challenge our most fundamental beliefs about space, time, and reality, pushing the boundaries of what we thought was possible. As research continues to evolve, the answers to these profound questions may one day reshape not only our understanding of the universe, but also the very nature of existence itself. Moreover, quantum foam presents profound and fascinating questions about the very fabric of reality itself. This concept challenges our traditional understanding of the universe, suggesting that the stable, solid objects and forces we perceive in our daily lives might be the result of a far more dynamic and fluctuating foundation within the fabric of space-time. At this level, space-time is not the calm, smooth continuum we often imagine, but instead a tumultuous sea of quantum fluctuations. This realization calls into question the nature of everything from matter to energy, urging us to reconsider the very building blocks of our universe. The existence of quantum foam implies that the cosmos may be far more complex and layered than what we can observe with the naked eye. What seems stable and predictable on a macroscopic scale may, in reality, arise from the chaotic interactions at the quantum level. Delving into the mysteries of quantum foam holds the potential to unravel the hidden dynamics governing the cosmos. It could bring us closer to a unification of quantum mechanics and general relativity, two fundamental pillars of modern physics that have remained stubbornly separate. Understanding this quantum froth might be the key to unlocking new realms of knowledge, possibly paving the way for groundbreaking discoveries that would radically transform our grasp of the universe. In recent years, researchers have turned their attention to the possibility of testing the existence of quantum foam, though this remains a daunting challenge. If scientists can develop techniques to observe its effects, it could provide invaluable insights into the origins of the universe itself and the fundamental forces that shape its evolution. The pursuit of understanding quantum foam is more than just an intellectual exercise. It represents the very heart of humanity's quest to decode the deepest mysteries of existence. As scientists continue their exploration, they are embarking on an extraordinary journey that could redefine everything we know about reality. On a completely different frontier, warp drive technology has captured both the imaginations of science enthusiasts and the serious interest of physicists alike. This concept, at its core, suggests the possibility of traveling faster than light, a feat long considered impossible within the bounds of conventional physics. At the heart of warp drive is the revolutionary idea of bending or warping space-time itself. Instead of propelling a spacecraft through space as we understand conventional motion, this technology proposes manipulating the space around it, creating a kind of bubble that propels the spacecraft forward. This method would theoretically allow for faster-than-light travel, all while adhering to the laws of physics. The inspiration behind warp drive draws heavily from Einstein's theory of relativity, which asserts that as an object approaches the speed of light, its mass grows infinitely large, requiring an impossible amount of energy to accelerate further. Warp drive, however, offers an elegant workaround to this conundrum. Instead of increasing speed, the spacecraft would essentially stretch the space behind it and compress the space in front of it. This theoretical warping of space could allow us to traverse vast cosmic distances in a fraction of the time it would otherwise take. One of the most well-known ideas connected to this possibility is the Alcubierre drive, which presents a concrete theoretical model for how this kind of faster-than-light travel might be achieved. Although warp drive currently belongs squarely within the realm of theoretical physics, recent advances in our understanding of quantum mechanics, gravity, and cosmic structures may hold the key to turning this idea into a tangible reality. Some scientists are already investigating the energy conditions necessary for such technology, with an eye toward producing negative energy density, an essential requirement for creating the warp bubble. While the notion of warp drive may still sound far-fetched, it serves as more than just a theoretical curiosity. It is a vehicle for driving innovation in propulsion technologies, and its study could yield entirely new ways to approach space travel. The implications of warp drive stretch far beyond speed. They prompt profound questions about humanity's future. Could it enable interstellar colonization? How would it affect our understanding of time itself? What would be the impact on our place within the cosmos? As scientists continue to explore these possibilities, they remind us that we are merely at the dawn of this ambitious journey. Many challenges lie ahead, but each step forward could potentially revolutionize how we explore space and deepen our relationship with the universe. Chaos theory offers yet another fascinating perspective, one that reveals the unpredictable and often intricate nature of complex systems, such as those found in the cosmos. At its essence, chaos theory shows that even the smallest changes in initial conditions can lead to vastly different outcomes over time. This principle has deep implications when studying cosmic events like the formation of galaxies or the dynamic behavior of celestial bodies. Consider the formation of a galaxy. Even the tiniest variation in the speed or position of a single star can create ripple effects, influencing the trajectory of nearby stars and altering the larger structure in unpredictable ways. These seemingly minor shifts can ultimately change the entire path of galaxy evolution. In fact, when we look at the universe as a whole, we see a vast network of intricately interconnected structures, from spiraling galaxies to enormous clusters of stars. Despite their apparent order, these structures emerge from chaos, driven by gravity, radiation, and other cosmic forces that operate on both large and small scales. Astrophysicists often apply chaos theory to study these phenomena, modeling everything from planetary movements to the collision of galaxies. These models reveal how slight changes in the initial conditions of a system can drastically alter its evolution. Take the collision of two galaxies, for example. This process can unfold in a variety of ways. It might lead to the birth of new stars, the ejection of stars into intergalactic space, or even the formation of entirely new cosmic structures. Chaos theory, in this context, helps us understand not just the static structure of the universe, but also its dynamic evolution over billions of years. Ultimately, chaos theory serves as a framework for understanding the rich diversity and unpredictability of the cosmos. It helps us make sense of the universe's infinite variety, from the tiniest planet to the largest galaxy cluster. Even as we uncover patterns and structures, we must remember that the universe is governed by a delicate interplay of order and chaos. This balance gives rise to the stunning array of phenomena we observe in the cosmos, offering us a glimpse into the underlying processes that drive the ever-changing dynamic nature of our universe. Lastly, the concept of artificial wormholes introduces another captivating idea within the realm of theoretical physics. Wormholes, often depicted in science fiction, are theoretical passages through space-time that could connect distant regions of the universe, or even different universes entirely. If we could artificially create such structures, the possibilities would be extraordinary. Instant travel across vast intergalactic distances, or the ability to send signals faster than the speed of light. However, the creation of artificial wormholes remains purely speculative at this point, and the challenges involved are enormous. One of the primary hurdles is the need for exotic matter to stabilize a wormhole and keep it open. This exotic matter would need to possess negative energy density, a concept that is still purely theoretical and well beyond our current understanding of physics. Without such matter, any wormhole created could collapse under its own gravity, preventing anything from passing through. Even if scientists were to overcome this barrier and create a stable wormhole, and the implications of such a discovery would raise profound questions. What would happen to objects traveling through a wormhole? Would they emerge intact on the other side, or would they be destroyed by the immense forces at play? These are just some of the numerous uncertainties that make the quest to understand wormholes both exhilarating and daunting. While the idea of artificial wormholes is still a distant dream, the pursuit of this possibility continues to fuel scientific inquiry. As we inch closer to understanding the very nature of space-time, we may one day unlock the key to a completely new form of travel and communication, transforming our understanding of the universe and our place within it. Furthermore, if wormholes could be harnessed for travel, the dangers of paradoxes and unforeseen consequences loom large. The very idea of using these shortcuts through space and time raises questions that have long puzzled both physicists and philosophers. For instance, the potential for time travel via wormholes opens up a vast array of scenarios where cause and effect could become tangled in ways that defy our understanding of reality. The consequences of such entanglement could lead to paradoxes, phenomena that scientists are still striving to fully comprehend. These are not just theoretical concerns. They represent genuine challenges that must be tackled before any meaningful progress can be made in the realm of wormhole travel. Despite these daunting obstacles, the pursuit of artificial wormholes has spurred unprecedented innovation in physics and cosmology. Researchers are not only seeking to answer fundamental questions about the nature of space and time, but also to push the very limits of what is scientifically possible. The mere idea of wormholes encourages a deeper exploration of the universe, enticing scientists to test the boundaries of known physics and question what might lie beyond. As we continue to probe the mysteries surrounding space-time, it becomes increasingly clear that our understanding is far from complete. Who knows? Perhaps one day, the fantastical idea of traversing vast cosmic distances through artificial wormholes will transition from the realm of science fiction to a tangible reality, merging our dreams of space travel with the core principles of the cosmos. In a similar vein, the concept of time loops, once confined to the pages of science fiction novels, has found new traction within the field of theoretical physics. As our understanding of the universe evolves, these captivating possibilities have emerged directly from the intricate fabric of space-time, as predicted by Albert Einstein's theory of relativity. According to relativity, time is not a simple, constant flow. Instead, it bends and warps in response to gravity and velocity, suggesting that time itself is malleable. This revolutionary idea has led to further exploration of scenarios in which time may loop back on itself, creating the conditions for events to repeat or change. Recent advancements in theoretical physics have prompted scientists to seriously consider the existence of closed time-like curves, pathways through space-time that could theoretically allow someone to revisit a moment in their past, or even alter the course of history. The implications of such phenomena are profound, challenging our fundamental understanding of causality and the very nature of reality. These discussions often hinge on the notion of exotic matter or theoretical constructs such as wormholes, hypothetical passages through space-time that could provide shortcuts not just across vast distances but through time itself. While the concept is tantalizing, it also presents immense theoretical and practical challenges. One of the most famous paradoxes associated with time travel is the grandfather paradox, which proposes that a time traveler could prevent their own existence by altering events in the past, thus creating an endless loop of contradictions. Beyond these theoretical explorations, developments in quantum mechanics have further fueled the intrigue surrounding time loops. Certain interpretations of quantum theory suggest that particles can exhibit behaviors that defy our traditional understanding of time. Quantum entanglement, for instance, describes a phenomenon where particles become linked in such a way that the state of one particle immediately affects the state of another, regardless of the distance between them. This suggests a deeper, more intricate layer of reality, one where time may not be linear or absolute. The implications of these findings are mind-boggling, hinting at a universe far more interconnected than we can fully grasp. As theoretical physics continues to advance, ideas about time loops invite researchers to contemplate a reality where the boundaries between past, present, and future are far more fluid than we ever imagined. These theories not only challenge our understanding of time, but also provoke profound questions about the nature of existence itself. How do we define reality when time itself might be a more complex and mutable construct than we thought? What does this mean for our understanding of cause and effect, of free will, and of the laws that govern everything we observe? Adding another layer of mystery to the cosmos is the concept of dark flow, a phenomenon that has raised intriguing questions about the nature of cosmic motion. This concept suggests that the universe, despite its apparent vastness and randomness, may be influenced by forces we cannot yet observe. Astronomers have noted that certain groups of galaxies, particularly those within the observable universe, are not simply moving due to the expansion caused by the Big Bang. Instead, they seem to be drifting in a particular direction, hinting at the presence of a massive, invisible force acting on them from beyond our observational reach. The existence of dark flow challenges our understanding of the cosmos in a fundamental way. The prevailing theory in cosmology holds that the universe, when viewed on a large enough scale, is isotropic and homogeneous. Isotropic means that the universe looks the same in all directions, and homogeneous means that matter is distributed evenly across it. Yet the discovery of dark flow suggests that the universe may not be as uniform as we once thought. Instead, it implies that there are vast, unseen structures, perhaps even entire galaxies or clusters of galaxies, beyond the limits of the observable universe, exerting a gravitational pull on the visible matter within our cosmic horizon. This intriguing idea opens up new questions about the structure of the universe and its overall design. If there are forces at play beyond what we can detect with our current technology, what else might be hidden from view? And what might we find as our instruments and understanding continue to evolve? The notion of dark flow invites us to reconsider the limits of our perception, pushing us to explore the unknown corners of the universe in search of answers. What lies beyond the observable universe, and how might it reshape our understanding of the cosmos and our place within it? These questions are as profound as they are elusive, and they are only the beginning of a much larger conversation about the nature of reality itself. Moreover, the enigmatic phenomenon of dark flow could potentially point toward the existence of vast, unexplored superclusters, or even entire universes nestled within a larger multiverse framework. This tantalizing possibility suggests that cosmic forces we cannot see, let alone comprehend, might be silently shaping our reality, pulling at the very fabric of our universe. The notion that we might be subtly influenced by cosmic entities, vast and invisible, beyond our reach and understanding, forces us to reconsider the narrative we have long held about the cosmos. This shifting perspective presents a profound challenge to scientists, urging them to rethink everything from the dynamics of gravity to the intricate structure of the universe. As they probe deeper into these hidden patterns, they are confronted with the compelling possibility that the universe may not be the orderly, predictable place we once assumed. Instead, it could be a far more complex, layered reality than we ever imagined, where the laws we once thought immutable might bend and shift in ways we cannot yet fully explain. The concept of dark flow, with its hints of mysterious forces at work, invites us to appreciate the immense complexities still veiled within the very essence of the universe. It reminds us that, despite the impressive strides we have made in understanding the cosmos, there are still deep, unsolved mysteries lurking beneath the surface. As researchers continue to gather data and refine their models, our understanding of cosmic motion may evolve, revealing an interconnected universe far more intricate and multifaceted than we ever thought possible. This ongoing investigation into dark flow is not just an academic pursuit. It is a testament to the boundless curiosity and relentless pursuit of knowledge that drive our ever-expanding horizons in cosmology. In this age of technological advancements, the tools available to us have revolutionized the way we explore the universe. Our understanding of the cosmos has been fundamentally transformed by innovations in telescope technology, which have allowed us to peer deeper into space than ever before. The leap from traditional optical telescopes to highly advanced instruments like radio telescopes and space-based observatories has unlocked the secrets of the universe that were once completely out of reach. These cutting-edge instruments extend our ability to observe the cosmos across an ever-widening spectrum of wavelengths, capturing more light and offering sharper, more detailed images than previous generations of telescopes could ever have dreamed of. Take, for instance, the Hubble Space Telescope, which has been operating in orbit for more than 30 years. Hubble's groundbreaking discoveries, such as its breathtaking images of distant galaxies and nebulae, have reshaped our understanding of the universe. Its ability to detect ultraviolet and infrared light has opened windows into celestial phenomena that are invisible to the naked eye, enabling scientists to observe processes that unfold in the farthest reaches of space. More recently, the James Webb Space Telescope has taken this capability to new heights. Positioned far beyond the interference of Earth's atmosphere, Webb's infrared vision allows us to look back in time, peering into the ancient past of the universe, even to moments just after the Big Bang. With this unparalleled perspective, Webb is providing scientists with unprecedented insights into the formation of stars, galaxies, and other cosmic structures, reshaping our understanding of the early universe. Meanwhile, radio telescopes like those at the Very Large Array in New Mexico are uncovering even more secrets of the cosmos. These massive, highly sensitive instruments allow researchers to study objects in space that emit radio waves, such as pulsars, and the cosmic microwave background radiation. This data is crucial for piecing together the story of cosmic evolution, shedding light on fundamental questions, such as the expansion of the universe and the nature of dark matter and dark energy. Looking ahead, the next generation of astronomical projects promises to push the boundaries of our observational capabilities even further. For example, the Square Kilometre Array, an ambitious project that will span South Africa and Australia, will provide unprecedented levels of sensitivity and resolution, taking us even deeper into the mysteries of the universe. By harnessing these state-of-the-art technologies, we are not simply expanding our understanding of the cosmos. We are actively rewriting the very story of the universe itself, one discovery at a time. Each new observation reveals more about the grand interconnected structure of space-time, and with every technological breakthrough, we uncover previously hidden layers of the cosmic tapestry. Equally pivotal in our quest to understand the universe are space probes, which serve as our eyes and ears in the vast, uncharted regions of deep space. These unmanned spacecraft are specifically designed to travel beyond Earth's protective atmosphere, carrying out scientific investigations in parts of the universe that are unreachable by human hands. Equipped with specialized instruments, space probes are able to collect invaluable data about distant celestial bodies, explore the atmospheres of gas giants, and even gather samples from asteroids and comets. By investigating these far-off regions, space probes help us unlock the secrets of our solar system and beyond, advancing our understanding of the very forces that govern the cosmos. Space probes serve a multitude of critical functions. For example, they map planetary surfaces, analyze atmospheric compositions, and observe the weather patterns of planets such as Mars. Advanced missions, like those conducted by the Mars rovers, provide insights into the history of water on Mars, while studying soil and rock samples for signs of past or present life. Other probes, like NASA's New Horizons, have ventured into the icy outer reaches of the solar system, sending back invaluable data from Pluto and the Kuiper Belt, an area that is still largely unexplored. These missions are helping scientists piece together the evolutionary story of our solar system and its celestial inhabitants. Looking ahead, space probes are set to become even more sophisticated. With the integration of artificial intelligence, upcoming missions will be able to make real-time decisions, adapting to unforeseen challenges as they explore. Missions like those targeting Europa, one of Jupiter's moons, aim to explore subsurface oceans that may harbor life. Such explorations promise to dramatically expand our understanding of habitability in the universe and may hold the key to answering one of humanity's oldest questions: are we alone in the cosmos? As our technological capabilities continue to evolve, space probes will play an increasingly vital role in unraveling the mysteries of deep space. Not only do they return groundbreaking scientific data, but they also inspire future generations of explorers and scientists, igniting curiosity and wonder in the hearts of those who will one day build upon these discoveries. Each new mission brings us one step closer to understanding our place in the vast and ever-expanding universe. Space missions are integral to our broader quest for knowledge, enabling scientists to explore the farthest reaches of space and uncover mysteries that would be impossible to study from Earth. Atmospheric interference, light pollution, and other limitations of ground-based telescopes prevent us from observing certain cosmic phenomena in detail. But with space missions, we can send advanced instruments directly into space, bypassing these obstacles and capturing clear, unimpeded images of distant galaxies, nebulae, and other celestial entities. These missions help us understand the formation and evolution of stars and galaxies over billions of years, providing invaluable insights into the history of the universe itself. The instruments carried by space missions are designed to detect various forms of radiation and cosmic signals, giving us the tools to observe cosmic phenomena that are otherwise invisible. For instance, space telescopes positioned beyond Earth's atmosphere can capture sharp, high-resolution images of distant objects across multiple wavelengths, from visible light to infrared and ultraviolet radiation. This has allowed scientists to study the composition of distant galaxies, track the formation of stars, and probe the deep mysteries of the cosmos in ways that were once thought impossible. Through these missions, we continue to peel back the layers of the universe's history, one revelation at a time. Robotic spacecraft and landers are at the forefront of humanity's direct exploration of distant planets and moons within our solar system. Missions such as the Perseverance rover on Mars have become vital instruments in our quest for knowledge. By collecting samples, analyzing soil and rock compositions, and searching for signs of ancient life, these missions offer profound insights into the red planet's past. They also provide clues about Mars's climatic history, revealing how the planet may have once supported life. These discoveries, fueled by curiosity and innovation, ask more questions than they answer, sparking new investigations into the conditions that might have enabled life to thrive on Mars. Meanwhile, far beyond the surface of Mars, Saturn's moon Enceladus has drawn the gaze of scientists worldwide. The Cassini spacecraft, through its detailed exploration, revealed geysers that eject water vapor into space. These geysers suggest the presence of subsurface oceans, offering tantalizing hints that Enceladus may harbor conditions suitable for life. Each of these findings pushes the boundaries of our understanding, urging us to rethink the origins of life and to consider the possibility that the right conditions for habitability may exist beyond Earth. Yet space exploration does not stop at the edge of our solar system. Missions aimed at probing the far reaches of space are expanding our horizons and revealing the vast mysteries of the universe. One of the most profound advances in space research came from the Kepler Space Telescope, which radically transformed our understanding of planets orbiting other stars. It identified thousands of exoplanets, some of which exist in the so-called habitable zone, the region around a star where liquid water could exist on the surface of a planet. This discovery has opened up an entirely new realm of exploration, as we now know that other Earth-like worlds may be scattered throughout the galaxy, waiting to be studied. Each mission, whether focused on our solar system or beyond, adds a small piece to the greater puzzle of the universe. The tapestry of knowledge we are weaving slowly comes together, and with each discovery, the excitement grows. The complexity of celestial phenomena can be overwhelming, yet with each breakthrough, we inch closer to understanding the nature of our universe. The anticipation builds, and with it, the motivation to continue exploring, asking deeper questions, and searching for answers. Amid these remarkable achievements, the dream of human colonization of other planets is no longer confined to the realm of science fiction. It is steadily evolving into a tangible goal. The prospect of sending humans to live on Mars, the Moon, or even other celestial bodies is becoming more realistic with every passing year. Within this new era of space exploration, we may soon witness the first steps toward establishing permanent human settlements on distant worlds. The initial phase of these settlements will likely focus on small, self-sustaining habitats, where astronauts will conduct research, test new technologies, and refine the techniques required to support larger, long-term populations. One of the key innovations that will enable this bold leap forward is in situ resource utilization, the practice of using local resources to build and sustain life on another planet. Instead of relying on costly and logistically complex shipments from Earth, astronauts will use materials from the planet itself. On Mars, for example, habitats could be constructed from the planet's own regolith, a powdery soil that covers much of its surface. This innovation would not only make sustainable living possible, but also lay the foundation for larger, more expansive colonies in the future. As technology continues to evolve, we can expect groundbreaking advancements in life support systems, capable of recycling air and water with incredible efficiency. These systems will be essential for long-term habitation, enabling astronauts to thrive in the harsh conditions of space. Additionally, the cultivation of crops in controlled environments will allow settlers to produce their own food, reducing the need to rely on Earth for sustenance. This shift towards self-sufficiency is a crucial step in the creation of sustainable human habitats on other planets. However, the challenges of colonization go beyond the technical. Psychological adjustments to life far from Earth, as well as the risks posed by radiation and microgravity, will test the limits of human resilience. Yet, as we learn to adapt to these new environments, the dream of establishing a permanent human presence on other planets draws nearer. This journey will be about more than survival. It will be an exploration of the very essence of what it means to be human, as we expand our reach into the cosmos and forge new pathways for future generations. It will foster a spirit of discovery and wonder, resonating with the pioneering spirit that has driven humanity throughout history. At the same time, artificial intelligence is reshaping the landscape of astronomical research, offering powerful tools that enhance our capacity to analyze the vast amounts of data generated by space missions. The universe offers an overwhelming torrent of information, from the light waves streaming from distant stars to the subtle patterns of celestial movement. Traditional methods of data analysis have struggled to keep up with this deluge, but AI is stepping in to help us process and interpret these vast quantities of information. This technology allows astronomers to extract meaningful insights from the noise, unveiling the hidden mysteries of the cosmos. Each breakthrough, whether it is the discovery of a new exoplanet, the identification of water on distant moons, or the development of advanced life support systems for future colonies, takes us one step closer to understanding the universe. With each question answered, more arise, keeping the excitement alive and fueling our ongoing exploration of the cosmos. However, artificial intelligence, AI, algorithms have proven to be indispensable tools in navigating the vastness of cosmic data, sifting through enormous datasets to identify subtle trends and anomalies that might otherwise escape human attention. One particularly exciting application of AI in astronomy is galaxy classification. Traditionally, scientists have categorized galaxies based on their shapes, a task that demands painstaking observation and a significant investment of time. With the advent of AI, particularly through deep learning techniques, this process has been revolutionized. By training AI algorithms on existing labeled datasets of galaxies, AI systems can quickly identify and classify new galaxies in a fraction of the time it would take a human. This automation accelerates the pace of discovery, making it possible to explore previously overlooked regions of the universe more efficiently. But AI's capabilities don't end with classification. It plays an equally critical role in analyzing light curves, graphs that track the brightness of celestial objects over time. This type of analysis is crucial for discovering exoplanets, planets that exist outside our solar system. When an exoplanet passes in front of its host star, it causes a subtle dip in the star's brightness. By using AI to detect these minute fluctuations, astronomers can pinpoint new worlds with remarkable accuracy and speed. This powerful technology allows for deeper analysis of data from various space missions, offering new insights that were previously unimaginable. Beyond classification and discovery, AI is also proving indispensable in predicting astronomical events. By integrating AI with advanced simulations of cosmic phenomena, scientists are now able to predict events such as supernovae or gravitational waves with greater precision. As our understanding of the universe deepens, it becomes increasingly clear that AI is not just a tool, it's an essential partner in the quest to unlock the universe's mysteries. With AI by their side, researchers are uncovering new insights faster than ever before, pushing the boundaries of what is possible in space exploration. As humanity stands on the brink of a new era in space exploration, the concept of space mining and resource utilization opens up both vast opportunities and complex ethical dilemmas. The prospect of extracting valuable materials from asteroids, moons, or even distant planets promises to unlock a wealth of resources. However, it also raises profound questions about the ethical implications of such activities. Just as Earth has experienced the detrimental effects of resource extraction, such as pollution and environmental degradation, could these same consequences be repeated on other celestial bodies? How do we prevent the exploitation of environments that have remained unchanged for billions of years, such as those found on asteroids or the moon? Furthermore, the question of ownership and sovereignty over these resources looms large. According to the Outer Space Treaty of 1967, no nation can claim sovereignty over celestial bodies. Yet, as commercial ventures in space mining begin to take shape, questions of property rights are becoming more urgent. If a private company mines an asteroid, should the extracted materials be considered property? This dilemma presents a significant challenge not only to international law, but also to global relations. The discovery of extraterrestrial life, particularly microbial life, could further complicate these discussions. Should we alter our approach to resource extraction if life exists beyond Earth? If life is present, how do we balance our desire for resources with the potential moral implications of contaminating an environment that harbors life? Another critical issue is inequality. The potential wealth generated by space mining could create vast disparities between nations, especially between those with the technological capabilities to access space resources and those without. This divide raises questions about how to ensure that the benefits of space resources are distributed equitably. Should these resources be available to all, or will a few wealthy nations or corporations monopolize them? These are not hypothetical questions, but real challenges that require careful consideration by ethicists, scientists, and policymakers alike. To address these concerns, international collaboration will be key. Space exploration has historically been a domain where nations, despite their differences, have worked together to achieve common goals. By pooling resources, expertise, and funding, countries have been able to embark on ambitious projects that would have been impossible to undertake individually. The International Space Station, ISS, stands as a testament to this global cooperation. In this remarkable space laboratory, scientists from the United States, Russia, Europe, Japan, and Canada conduct experiments that not only advance space exploration but also contribute to life on Earth in areas like medical research, material science, and environmental monitoring. Moreover, international collaboration expands access to space for developing nations, allowing countries like India, Brazil, and South Africa to contribute to and benefit from global space projects. These nations bring unique perspectives and innovations to the table, fostering a more diverse scientific community. This inclusivity strengthens the global effort to solve universal problems and promotes peace and diplomacy through joint exploration initiatives. As these partnerships grow, they pave the way for ambitious long-term goals, such as Mars colonization or asteroid mining, both of which require vast investments and multinational teams. By working together, nations can increase the chances of success, moving humanity closer to unlocking the secrets of the cosmos. The future of space travel is on the verge of transformative breakthroughs, particularly in propulsion technology. One of the most exciting developments in this field is ion propulsion. Unlike traditional chemical rockets that rely on burning fuel, ion thrusters use electricity to accelerate ions, generating thrust in a highly efficient manner. This technology allows spacecraft to maintain a steady acceleration over extended periods, making it ideal for deep space missions. Another promising avenue is nuclear thermal propulsion, where a propellant like hydrogen is heated in a nuclear reactor and expelled through a rocket nozzle. The potential for higher efficiency and greater thrust could reduce travel times to distant destinations, such as Mars, from several months to just weeks. This could fundamentally change humanity's capacity for interplanetary travel. Looking even further ahead, researchers are exploring the tantalizing possibility of antimatter propulsion. When matter and antimatter collide, they release enormous amounts of energy, far exceeding the energy output of chemical rockets. Though still theoretical and requiring groundbreaking technological advancements, antimatter propulsion could enable spacecraft to travel at near-light speeds, drastically reducing travel times throughout the solar system. Lastly, solar sails. Lightweight, thin films that capture the sun's radiation pressure are also under investigation. These sails would require no fuel, relying solely on sunlight to propel spacecraft, making them an exciting alternative for long-duration space missions. With each of these developments, humanity stands on the edge of a new era in space exploration. Propulsion technology continues to evolve, pushing the boundaries of what is possible and bringing the stars within reach. Space tourism is another emerging frontier, offering an intersection of adventure and education. As commercial space travel becomes more accessible, it allows ordinary people to experience the wonders of space firsthand. Tourists can gaze upon Earth from above, float in microgravity, and witness the vastness of the cosmos. These experiences can profoundly alter our understanding of our planet's fragility and the complex systems that sustain life. When space tourism becomes more widespread, it has the potential to ignite a broader public interest in astrophysics, space exploration, and astronomy. Individuals who once felt disconnected from these fields may become inspired to engage with them more deeply. Furthermore, space tourists will likely share their experiences with the world, whether through social media or public talks, fostering a new cultural appreciation for space. This shared excitement may encourage society to prioritize space study and protection. The experience of seeing Earth from space, known as the overview effect, has a profound emotional impact on astronauts, offering them a fresh perspective on the beauty and fragility of our planet. This phenomenon could inspire positive social and environmental change, urging humanity to act more responsibly toward our planet and its place in the vastness of the universe. As public interest in space tourism grows, so too will the demand for scientific research and funding for space exploration. With greater awareness, individuals may rally behind projects that seek to solve the universe's mysteries, from discovering new planets to understanding the formation of galaxies. This shift in focus could propel a new generation of explorers, driven by a deep desire to expand humanity's reach into the cosmos. Astronomers continue to probe the deepest mysteries of the universe, one of the most pressing being the nature of dark energy. This mysterious force, believed to be responsible for the accelerated expansion of the universe, holds the potential to fundamentally alter our understanding of cosmic evolution and the ultimate fate of the universe. Another key area of exploration is the search for life beyond Earth. Missions like the James Webb Space Telescope are studying exoplanets in habitable zones, seeking signs of biological activity. The discovery of microbial life on another planet would not only reshape our understanding of biology, but challenge our philosophical views on humanity's place in the cosmos. The study of black holes is another captivating frontier. Recent breakthroughs have enabled astronomers to capture images of black holes and study their effects on nearby matter. The goal is to unlock the mysteries of these cosmic giants, which play a pivotal role in shaping galaxies. Understanding black holes could also shed light on the fundamental laws of physics, such as how they relate to quantum mechanics and general relativity. Finally, the cosmic microwave background, the afterglow of the Big Bang, remains a vital source of information for understanding the early universe. By analyzing this relic radiation, scientists hope to gain new insights into the universe's origins and its future trajectory. As our technological capabilities grow and our ability to observe the universe improves, these questions will undoubtedly lead to groundbreaking discoveries that will reshape our understanding of the cosmos. Each revelation brings us closer to unlocking the ultimate mysteries of the universe, offering an ever clearer picture of where we come from and where we are headed next.